We think of ice as something simple, solid, a fixed point in a changing world. We see it as the definition of frozen, of something locked in place. But this simplicity is not the whole story. What if I told you that every piece of ice has a quiet, internal motion? A restlessness that comes not from external heat, but from its own nature. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is not about the pressure from a skate or the friction from a boot, the story that has been told for a very long time. This is about a microscopic, liquid-like skin that covers all ice. A layer that makes ice one of the most dynamic and complex substances on Earth. This hidden quality does more than explain a slip on a frozen path. It scales up to explain why entire continents of ice may be less stable than they appear. By the end of this, you will look at ice in a new way. The order of ice. Let's begin with the ice we think we know. It is a substance of profound geometric beauty. When you cool pure water, you witness a quiet transformation. The water molecules, which in their liquid state are in constant, disordered motion, begin to slow. As they approach 0 degrees Celsius, they stop their chaotic movement and begin to settle into their designated places. Each water molecule, H2O, is polar. The oxygen atom holds a slight negative charge, and the 2 hydrogen atoms hold a slight positive charge. This makes each molecule like a tiny, weak magnet. As they cool, these small magnets attract each other, positive end to negative end, forming what are called hydrogen bonds. These are not the strong bonds that hold the molecule itself together. They are more like a gentle but persistent connection between neighbors. What these connections lack in individual strength, they make up for in collective structure. They arrange themselves into an ordered, 3-dimensional crystal. Specifically, the ice you encounter every day, known as ice IH, forms a hexagonal lattice. Imagine a repeating honeycomb pattern extending in all directions. Each water molecule is perfectly positioned, held at a specific distance and angle by those hydrogen bonds. This structure is precise. It's the reason why no 2 snowflakes are identical, yet all of them share a fundamental 6-sided symmetry. Each snowflake is a unique expression of this underlying hexagonal rule. This crystal structure has a well-known consequence. Unlike most other substances, which become denser when they freeze, water expands. The hexagonal lattice is an open structure with empty space between the molecules. It takes up about 9% more room than the same molecules in their liquid state. This is why ice floats. It is also why lakes freeze from the top down, creating an insulating layer that allows life below to survive the winter. Without this quality, life on Earth might look very different. So, this is our starting point. A substance built on a foundation of crystalline order. Rigid, brittle, a quiet solid. This is the ice we think we know. And yet, this perfect structure holds a contradiction. One that begins with a simple question. Why is it so slippery? The 200-year-old idea. The question of ice's slipperiness has been a puzzle for a long time. It is counterintuitive. Most hard, rigid solids are not slippery. They generate friction, yet a blade on a sheet of ice glides with an unusual ease. For a long time, the explanation seemed as elegant as the crystal itself. The idea that took hold in the 19th century is known as pressure melting. It was proposed by James Thomson, who built on a principle of thermodynamics. We know that water expands when it freezes. Therefore, applying pressure to ice should encourage it to take up less space. And the form of water that takes up less space is liquid. The theory stated that applying pressure to ice lowers its melting point. The logic is appealing. An ice skater's weight on a thin blade creates immense pressure. This pressure, the theory proposed, melts a microscopic layer of ice directly beneath the blade. The skater glides on this self-generated film of water. When the skater moves on, the pressure is released, and the water refreezes. This process is called regulation. You may have seen it demonstrated with a wire and weights appearing to pass through a block of ice, leaving the block whole. It's a compelling story. It feels correct. There is just one problem. When the mathematics were examined, the explanation began to fall short. To lower the melting point of ice by just 1 degree Celsius, you need to apply about 133 times normal atmospheric pressure. An average 75 kg skater exerts a pressure of about 1.2 megapascals, which is significant, but it only lowers the melting point by about 1/10 of a degree. It is simply not enough to explain skating on an ice rink kept at -5 degrees Celsius. Another idea suggested that the heat from friction was the cause. Frictional heat does play a role, especially for an object already in motion. But it cannot explain why ice is slippery even when you are standing still. It also struggles to account for slipperiness at very cold temperatures, where any heat would be quickly absorbed by the surrounding ice. So, we are left in an interesting place. The most common explanations are not sufficient. Pressure melting is mostly a myth. Frictional heating is only part of the story. The true reason for ice's instability is more subtle. It lies not in what we do to the ice, but in what the ice is already doing to itself. The real secret. A liquid skin. The first clue to the real nature of ice came not from a complex theory, but from a simple observation made by the physicist Michael Faraday in the 1840s. He pressed 2 ice cubes together and saw that they fused into a single block, even in a room kept below freezing. He reasoned that the cubes were coated in a thin, invisible film of water. He called this pre-melting, suggesting the surface of ice was not truly solid, but existed in an unfinished state. Faraday's intuition was correct. He had discovered what is now known as the quasi-liquid layer. For over a century, his idea was mostly overlooked. But with modern surface science, we have been able to look at the surface of ice with new clarity. And what we have found is that the surface is not a perfect continuation of the crystal within. It is a disordered, mobile layer. This isn't true liquid, and it isn't true solid. It's a transitional phase, just a few molecules thick. It is a skin that exists on the surface of ice, even at temperatures far below freezing. Experiments have confirmed its existence down to around -40 degrees Celsius, and some evidence suggests a form of it persists at far lower temperatures. This is not melting in the usual sense. It is an intrinsic feature of ice's structure. This happens because the molecules at the surface are incomplete. Deeper within the crystal, each water molecule is comfortably connected to 4 others. But a molecule at the very surface has nothing above it. It has unfulfilled bonds. These surface molecules are less stable. They are moved by thermal energy, and they twist and shift out of the rigid lattice structure, breaking the perfect order. There is also a more subtle electrical effect. The molecules in an object touching the ice can disrupt the delicate order of the surface, adding to the disorder. The crystal is being gently disorganized at the interface. This quasi-liquid layer is the key to understanding ice. It acts as a lubricant, a layer of molecular ball bearings that allows objects to glide over it. The properties of this layer also change with temperature. Just below freezing, the layer is thicker and more watery, creating a very slick surface. At the colder temperatures of a hockey rink, often around -9 degrees Celsius, the layer becomes thinner and more viscous, providing more grip for sharp turns. This single concept, that ice wears a permanent, self-generated liquid skin, replaces older, incomplete explanations. It shows that ice is not a passive solid. It is an active surface, constantly in a state of partial disorder. This microscopic instability is the true reason ice is so slippery and so interesting. If this kind of calm exploration into the world around us helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a frozen lake, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Now, let's see how this concept of a microscopic instability scales up to create changes that are anything but microscopic. The unstable giant. From slips to continents. We have just explored a quiet instability measured in nanometers. It is easy to see it as a simple curiosity. But the same underlying qualities of ice, the gentle hydrogen bonds and the incomplete geometry at its boundaries, are woven into the fabric of ice on every scale. When you move from a sheet of ice on a pond to a sheet of ice the size of a country, this structural quality has vast consequences. Consider a bridge pier in a frozen river. For a long time, engineers have observed a strange phenomenon. When a massive, slow-moving ice sheet pushes against a structure, you might expect a steady force. But instead, the structure often begins to vibrate. This is because the ice does not fail in a simple, brittle way. At the point of contact, a complex zone of micro-fracturing and recrystallization forms. The ice in this zone softens, yields, and then briefly recovers its strength in a repeating cycle. The ice sheet begins to pulse against the structure. If this pulse matches the structure's natural frequency, the vibrations can become catastrophic. Ice, the rigid solid, becomes a dynamic force. This capacity for ice to change its internal state is central to understanding the largest ice sheets on Earth. In West Antarctica, the glaciers are kilometers thick. Much of this ice rests on bedrock that is below sea level, and this bedrock often has a retrograde slope, meaning it gets deeper further inland. These glaciers flow slowly toward the ocean, extending over the water as vast, floating ice shelves. The point where the glacier lifts off the bedrock is called the grounding line. The ice shelves act as a buttress, slowing the flow of the glacier behind them. For a long time, this system was in relative balance. But now, warming ocean water is melting these ice shelves from below. As they thin, they provide less support, and the glaciers behind them speed up. This causes the grounding line to retreat inland. This is where the retrograde slope can trigger a self-reinforcing process. This is the marine ice sheet instability (MISI) hypothesis. As the grounding line retreats into deeper water, the ice flow increases. This faster flow stretches and thins the upstream ice even more, which in turn causes the grounding line to retreat further. It is a feedback loop that, once triggered, is believed to be irreversible. We are already seeing evidence that this process may have begun in critical glaciers like Thwaites and Pine Island. There is a related idea that could accelerate this process: marine ice cliff instability. Michi, asterisk. This hypothesis suggests that if an ice shelf completely disintegrates, it leaves a sheer, vertical cliff of ice at the water's edge. Any material has a structural limit to how tall a vertical cliff can be before it collapses under its own weight. For ice, this limit is thought to be around 90 meters above the waterline. If an exposed cliff is taller than this, it may become structurally unstable. It would not just calve icebergs, but could begin to fail catastrophically, with huge sections collapsing. This would trigger a process of rapid retreat, far faster than predicted by MISI alone. It is the ultimate expression of ice's internal structural weakness. Our journey began with the idea of ice as a simple, unchanging solid. We saw how early explanations for its slipperiness gave way to a more subtle reality: a thin, liquid-like layer that is an intrinsic part of its nature. This small-scale motion does not remain small. It informs the behavior of ice on a vast scale, from the vibrations in a frozen river to the stability of the colossal ice sheets of Antarctica. Ice, it turns out, is most unstable at its boundaries. At the surface where it meets the air, and at its edges where it meets the sea. We think of it as a static substance, but it is one of the most complex and dynamic materials on our planet. The next time you drop an ice cube into a drink, remember the quiet restlessness hidden within it. You are not just looking at frozen water. You are looking at a substance in a state of constant, subtle change, a reminder that even the most solid things in our world are still in motion. The secret weakness in ice that saved the world. Ice. It is one of the most powerful forces on our planet. A shaper of mountains, a sculptor of valleys. We see its strength in the vast, frozen landscapes of the Arctic and Antarctic, and in the colossal icebergs that dwarf ocean liners. It feels like a symbol of permanence, of a world held still. But it has a secret. A fundamental property buried in its very structure that seems like it should make it unstable. A quality so profound, it steps away from a basic pattern that nearly every other substance in the universe follows. This quiet deviation is one of the key reasons that life, in all its chaotic, beautiful complexity, was able to get started on this planet at all. The story of life on Earth isn't just written in rock and fossil. It's written in the very structure of a single, humble ice crystal. And to understand it, we have to unlearn something we think we know about the solid world. If this kind of calm exploration into the science that shapes our world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share a memory you have of ice or snow, something that this story brings to mind. The universal rule breaker. In the universe, there are patterns. Laws of physics that govern the behavior of everything from the smallest atom to the largest galaxy. One of the most intuitive of these patterns concerns how things change with temperature. When things get hot, they expand. Their atoms and molecules gain energy, vibrating and pushing each other apart, taking up more space. When things get cold, they contract. The energy drains away, the movement slows, and the atoms and molecules huddle closer together, packing themselves into a smaller volume. This is the principle of thermal contraction. It's a rule that is followed with almost perfect obedience across the known universe. Think about molten steel. It's a turbulent, flowing liquid. As it cools, its iron atoms slow down, their chaotic movement ceasing as they lock into a rigid, crystalline structure. And as they do, they pack together more tightly. A solid bar of steel is denser than the molten liquid it came from. If you could drop a solid piece of steel into a vat of molten steel, it would sink straight to the bottom. The same is true for almost every substance you can imagine. Solids are denser than their liquids. This is the rule. Now, consider a glass of water. You drop in a few ice cubes. And they do something that should be impossible. They float. This simple, everyday observation is so common that we rarely think about it. But in the grand theater of physics, it is a moment of quiet rebellion. Water, in its solid form, is less dense than its liquid form. It breaks the universal rule. When water freezes, it doesn't contract. It expands. It pushes outward with enormous force, strong enough to crack engine blocks and shatter boulders. This expansion is about 9%, meaning a liter of water becomes about 1.09 liters of ice. This makes ice lighter than the water it displaces, and so it floats. This isn't just a curiosity. It is one of the most important anomalies in all of science. It's a property so strange and so critical that without it, the entire history of our planet would have been completely different. Life, as we know it, would likely not exist. The Earth could have become a permanent snowball, a frozen, lifeless rock hurtling through space. So why does water get to play by a different set of rules? What is happening in the hidden, microscopic world of water molecules when the temperature drops to zero? The answer is not just a scientific detail. It may be the key to our very existence. To find it, we must journey down to the level of the atoms themselves, to witness a strange and beautiful dance that choreographs the fate of our world. The journey to the molecular dance floor. To understand ice's secret, we have to start with the building block itself, a single molecule of water. Its chemical formula is H2O. Two hydrogen atoms bonded to one oxygen atom. But the asterisk way they are bonded is the source of all of water's unusual properties. Imagine the oxygen atom as a large sphere. The two hydrogen atoms are attached at an angle, making the molecule look a bit like a V-shape. This bent shape is absolutely crucial. The large oxygen atom has a much stronger pull on the shared electrons in the bonds than the small hydrogen atoms do. This means the electrons spend more time around the oxygen atom, giving it a slight negative charge. The two hydrogen atoms, in turn, are left with a slight positive charge. This makes the water molecule polar. It has a negative end and a positive end, much like a tiny, weak magnet. This polarity is everything. In liquid water, these tiny molecular magnets are all jumbled together, constantly moving past one another. The positive end of one water molecule is attracted to the negative end of another. This attraction is called a hydrogen bond. It's important to understand what a hydrogen bond is. It's not the primary, incredibly strong bond that holds the H2O molecule together. A hydrogen bond is a much weaker force between molecules. Think of it like a group of people in a crowded room briefly holding hands. They can connect and let go easily. In liquid water, the molecules have a lot of thermal energy. They are zipping around, vibrating and rotating in a chaotic dance. Hydrogen bonds are forming and breaking in a frenzy, lasting only for a few trillionths of a second. In this state, they can get quite close to one another, like a disorganized but tightly packed crowd. This is liquid water in its dense, fluid state. As you begin to cool the water, you are removing energy. The dance starts to slow down. The molecules move less vigorously, and the hydrogen bonds last a little longer. As water cools from room temperature down to 4 degrees Celsius, 39.2 degrees Fahrenheit, it behaves like any other substance. The molecules slow down, pack in a little tighter, and the water becomes denser. This is why the coldest, densest water in a lake is often at the bottom. But then, something remarkable happens. As the water cools below *4 degrees Celsius, the trend reverses. The water actually starts to become less dense. This is the famous density anomaly of water. The slowing molecules are no longer just tumbling randomly. The hydrogen bonds are beginning to assert their influence, directing the molecules into a more ordered arrangement, guiding them toward their lowest energy state. The grand freeze, choreography of crystallization. Imagine a grand ballroom. In liquid water, the dancers are a disorganized, energetic crowd, moving freely and packing the floor tightly. As the music slows, as the temperature drops, the dancers begin to find partners and arrange themselves for a formal, choreographed dance. They are no longer a chaotic crowd, they are an organized formation. And a formal dance formation, with everyone holding their partners at a set distance, takes up much more space. This is what happens when water freezes. To achieve maximum stability, each water molecule wants to form exactly 4 hydrogen bonds with its neighbors. When the temperature hits 0 degrees Celsius, 32 degrees Fahrenheit, the music stops. The molecules finally have low enough energy to lock into this perfect, stable formation. They arrange themselves in a beautiful, repeating, 3-dimensional pattern, a hexagonal crystal lattice. In this lattice, the molecules are held at a fixed distance and a specific angle by these hydrogen bonds. This forces them into a very specific, rigid, and surprisingly open structure. And open is the critical word. This highly ordered crystalline structure has large empty spaces at the center of its hexagonal rings. The molecules are held at arm's length from each other, creating a structure that is significantly less dense than the jumbled arrangement of liquid water. This expansion is significant. The volume of the water increases by about 9% upon freezing. The density drops from about 1,000 kilograms per cubic meter for liquid water to about 917 kilograms per cubic meter for ice. This is the weakness at the heart of ice. Its solid form is built on a scaffold of hydrogen bonds that forces it to be spacious and less compact than its own liquid. This crystalline structure is not just an abstraction, you see its signature everywhere. The next time it snows, look closely at a single snowflake. You'll see that it has 6 sides or 6 points. That beautiful 6-fold symmetry is a direct, large-scale manifestation of the underlying hexagonal lattice of the ice crystals that form it. But this elegant structure, this source of its life-saving buoyancy, is also the source of its fragility. Those hydrogen bonds, while strong enough to create a solid lattice, are still relatively weak. Adding energy in the form of heat easily breaks them, causing the lattice to collapse back into the denser, disordered liquid state. This is melting. This inherent instability, this weakness, is 2 sides of the same coin. The very thing that makes ice float is what makes it susceptible to change. And it is this floating that has made all the difference. The revelation. A world without floating ice. Now, let us conduct a thought experiment. Let us imagine a parallel world where water behaves normally. When it freezes, it obeys the universal rule of thermal contraction. Solid water, ice, is denser than liquid water. What would this world look like? As the first winter arrives, the surface water of a deep lake cools, becomes denser, and sinks. This process would continue all the way to 0 degrees Celsius. The coldest, densest water would always be at the bottom. Then, the surface water would freeze. But this ice would be denser than the water beneath it. So, it would sink. It would drift down through the water column like a strange, crystalline snow, settling on the lakebed. At the surface, new water would be exposed to the frigid air, freeze, and sink in turn. This process would continue, relentlessly. The lake would begin to fill with ice from the bottom up. Aquatic life would face a catastrophic new reality. Plants rooted in the sediment would be crushed. Fish and other creatures would have nowhere to escape as the solid frost advanced upwards. By the end of a long, cold winter, the lake would be a solid block of ice. Then, summer would arrive. The sun would warm the surface of the lake, but sunlight can only penetrate so far. The thick mass of ice at the bottom would be shielded from the sun's warmth. While a thin layer at the surface might melt, the vast majority of the sunken ice would likely remain frozen. Year after year, the ice would accumulate. Over time, the lake would become permanently frozen. No complex aquatic life could survive there. Now, scale this up to a global level. The polar seas would begin to freeze, and the ice would sink. Vast quantities of the planet's water would become locked away on the ocean floor. This could trigger a powerful feedback loop. The growing expanse of sunken ice would cool the deep ocean currents, which in turn would cool the planet. This runaway effect could plunge the Earth into a snowball Earth state, a global glaciation from which it might never recover. Life, which began in the oceans, might have had no chance. The stable, liquid environment necessary for the slow, patient process of evolution would simply not exist. But that is not our world. In our world, the flaw in ice saves us. When winter comes to a lake on our Earth, the surface water freezes, and because this ice is less dense, it stays on top. It forms a sheet, a blanket, across the surface. This layer of ice is a fantastic insulator. It protects the liquid water below from the freezing air above. Beneath this icy shield, a world of life continues to thrive. The water remains liquid, hovering at a life-sustaining temperature just above freezing, with the densest water at 4 degrees Celsius settled at the very bottom. Fish swim, and an entire ecosystem is able to survive the winter, waiting for the spring thaw. The seasonal cycle of freezing and thawing is a rhythm of life, not a death sentence. Globally, floating sea ice at the poles acts as a giant mirror, reflecting sunlight back into space and helping to regulate the planet's climate. This unusual, floating ice is not a bug in the system. It is a central feature that makes our world a dynamic, living planet. We began with a simple observation: an ice cube in a glass of water. We called its ability to float a weakness, a flaw. But as we have seen, this quiet deviation from the norm is revolutionary. The secret isn't that ice is weak, it's that its unique structure redefines strength. The hydrogen bonds that force water molecules into an open, spacious, hexagonal lattice are the architects of our world. They create a solid that is less dense than its own liquid, a property so rare it feels deliberate. This flaw is a planetary life support system. It provides an insulating blanket for our lakes and seas, protecting aquatic life from the cold of winter. It ensures that our planet's water remains largely liquid and dynamic, driving the currents and climate systems that make Earth habitable. Without this property, our world could be a static, frozen museum. The oceans might be vast, solid tombs of sunken ice, and the story of evolution may have ended before it even truly began. The very instability of the ice crystal, its tendency to form a less dense structure, is the foundation for the stability of life on Earth. So the next time you drop an ice cube into a drink and watch it bob to the surface, take a moment to appreciate the profound truth you are witnessing. You are not just chilling your beverage. You are observing a quiet miracle of physics. You are seeing a silent testament to one of the most important weaknesses in the natural world. The weakness that became a superpower. The flaw that saved the world. And in that simple, floating cube, you can see the reflection of our own improbable existence, made possible by the beautiful, life-giving fragility of frozen water. Antarctica is collapsing from the inside out. For a long time, the story we told about Antarctica was a simple one. We pictured a frozen continent, distant and still, slowly yielding to a warming world from the outside. We saw warming air touching its surface. We watched warming oceans lap at its edges, breaking off immense pieces of ice into the sea. The story was clear, and it was visible. It was the story of a world melting from the outside in. But that was never the whole story. The continent held a deeper secret, one that has very little to do with the surface at all. What if the most important changes are happening from within? Scientists have found something miles beneath the ice that shifts our understanding of the continent, and of our future. A hidden world of water and rock, moving in ways we are only just beginning to see. Vast rivers, older than memory, are flowing deep within the ice, and they are beginning to quicken. This is not a story of a slow surface melt. It is the story of a dynamic, hidden world, one whose fate is connected to our own, and whose secrets we are just starting to understand. To appreciate the meaning of this discovery, we first need to remember the story we thought we knew. The Antarctic ice sheet is not just a layer of ice. It is a dome of frozen water the size of a continent, in some places nearly 3 miles thick. It holds most of the world's ice, and within it, enough water to change the shape of every coastline on Earth. For decades, the science of its change seemed straightforward. The first force was the atmosphere. As the world warms, we see more melting on the surface, creating brilliant blue lakes on the ice. These are not just puddles. Sometimes, the water drains down through cracks, a process called hydrofracturing. The weight of the water can wedge these cracks open, weakening the ice from the top down. The sudden disintegration of the Larsen B ice shelf in 2002 was a surprising example of this. It vanished in just over a month. The second, and more powerful, force is the ocean. Antarctica is edged by enormous floating platforms of ice called ice shelves. They act like a cork in a bottle, holding back the vast glaciers that flow from the middle of the continent. But the ocean around it is warming. A layer of warmer, saltier water, known as circumpolar deep water, is being pushed closer to the continent, and it flows beneath these floating shelves. This water eats away at the ice from below, thinning the shelves and making it easier for the glaciers behind them to slide forward. This outside-in story has been the foundation of our understanding for a long time. It is a story of an external process, with heat affecting the ice from above and from its edges. It is a real and important part of what is happening, but it is a slow process. The new evidence, however, points to something else. A hidden, internal world that has always been there, a world that is now being stirred by our changing climate, threatening to speed up this process from the inside out. The fortress, it turns out, was never solid. The idea of Antarctica as a solid block of ice on frozen ground is not correct. For many years, it was a blank space on the map. But a quiet technological revolution has allowed us to look beneath the ice sheet, and what we have found is breathtaking. It is not a static continent. It is a living, moving world. The breakthrough came from new ways of seeing. Scientists, using ice-penetrating radar on aircraft like those in NASA's Operation Icebridge, sent radio waves down through miles of ice. By analyzing the echoes that bounced back, they created a map, not just of the ice, but of the land buried beneath it. What they saw defied expectation. Beneath the ice lies an entire continent with mountain ranges and deep canyons. And woven through this hidden landscape is something even more surprising: liquid water. Not just small pockets, but a vast water system that spans the continent. Imagine a network of arteries not carrying blood, but meltwater buried under 2 miles of ice. Satellites have been essential in this discovery. They can measure tiny changes in the height of the ice surface. Scientists noticed that in some places, the ice would rise by several feet and then, months or years later, sink back down. There was only one explanation. A huge lake of water hidden below was filling up, lifting the ice sheet, and then draining away, causing the surface to fall. Through these methods, scientists have now mapped hundreds of these subglacial lakes. Many of them are active, meaning they fill and drain in cycles. These are not small ponds. The largest, Lake Vostok, is one of the biggest lakes on Earth, buried under more than 2 miles of ice. And these lakes are connected. The same data revealed complex plumbing systems that can move enormous amounts of water over hundreds of miles, from the deep interior of the continent out toward the ocean. This discovery changes everything. Antarctica is not a solid block being melted at its edges. It has a hidden circulatory system, a plumbing network that lubricates the base of the ice and influences how it flows. And this hidden world, which has existed for thousands of years, is now beginning to respond to new pressures. The question is no longer just, how fast will the oceans melt the ice? But, what happens when the continent's own hidden arteries begin to flow faster? A natural question follows. In a place where the average temperature is far below freezing, where does all this liquid water come from? The answer lies not in the sky or the ocean, but deep within the Earth itself. Antarctica may be covered in ice, but it is a continent like any other, with a warm, active geology. The main source of this warmth is geothermal heat. The Earth's crust naturally releases heat from its core and from the slow decay of elements in its rocks. This gentle, steady release of energy warms the base of the ice sheet. This heat varies across the continent. Near the South Pole, scientists from the British Antarctic Survey found an area where an unusual amount of geothermal heat is melting the ice from below. The source is thought to be a combination of radioactive rocks and hot water moving up from deep underground. This process has likely been happening for millions of years, slowly creating the water that fills the subglacial lakes. But there is another, more concentrated source of heat: volcanoes. West Antarctica, in particular, sits on a major volcanic rift system. The land here is being stretched, allowing magma to get closer to the surface. Using radar, scientists have uncovered a vast volcanic region hidden beneath the ice, with some studies identifying around 91 volcanoes. Many of these are dormant, but some may be active. One leading hypothesis suggests that a mantle plume, a narrow stream of hot rock rising from deep within the Earth, exists beneath Marie Byrd Land in West Antarctica. This persistent heat source would help explain the vast network of rivers and lakes found there. It's important to understand that these volcanoes are not about to erupt through the ice. Their influence is more subtle. They act like quiet heating elements at the base of the ice sheet. They create reliable sources of meltwater, keeping the subglacial plumbing system charged. This water lubricates the base of the ice, allowing the glaciers above to slide more easily toward the ocean. Think of the geothermal heat in volcanoes as the quiet engines of Antarctica's hidden world. They provide the constant energy that keeps the system alive. For thousands of years, this was a system in relative balance. But now, as external forces from a warming climate begin to interfere, this internal engine is helping to create a slippery, unstable foundation for the entire West Antarctic ice sheet, a foundation that is now beginning to move. The discovery of water under Antarctica was revolutionary, but the realization that this water was moving was a quiet paradigm shift. We are not just observing still pools of meltwater, we are witnessing the pulse of a continent. The active subglacial lakes are like the beating heart of this hidden world, filling and draining in cycles that can affect the ice sheet from its very base. Using satellites, scientists can watch the ice surface rise and fall, like the slow breathing of a sleeping giant. These are not small movements. Over some lakes, the ice surface can rise by 10 feet or more as they fill, and then drop just as dramatically when they drain. This constant flexing of ice that is miles thick creates stress, weakening its structure from within. Recent discoveries have shown just how widespread this is. Satellite data has steadily revealed new active lakes and interconnected networks, confirming that we are looking at a continent-wide, interconnected plumbing system. To understand this, we can look at two places that serve as windows into this hidden world: Lake Whillans and Blood Falls. Lake Whillans is a shallow, active lake under about half a mile of ice in West Antarctica. In 2013, a project successfully drilled into the lake. What they found was astonishing. Not only was the lake part of an active water system, but it was filled with life. They discovered a community of microbes living in total darkness, surviving on chemicals from the rock below. The existence of life in Lake Whillans proved that these environments are not empty voids, they are living ecosystems. Even more striking is the quiet phenomenon of blood falls. From the tongue of the Taylor Glacier, a plume of rust-red water periodically flows out, staining the white ice. For a long time, it was a mystery. We now know that this is extremely salty, iron-rich water coming from a subglacial system that has been trapped for up to 2 million years. The water is iron-rich but has no oxygen. When it finally reaches the atmosphere, the iron oxidizes, it rusts, instantly turning the water a deep red color. More than a curiosity, Blood Falls acts as a visible valve for the hidden plumbing. During one outflow event, trackers on the glacier surface measured a sudden change. As the brine was released, the pressure at the base of the glacier changed, and its forward motion slowed for a time. This was direct proof of what scientists had suspected. These drainage pulses are powerful enough to affect the massive glaciers above them. These lakes gather meltwater, store it, and then release it in large, hard-to-predict pulses. Each pulse sends a wave of lubricating water rushing toward the sea, quickening the flow of the ice above it. This constant filling and draining weakens the ice from within, and as we are about to see, these lake systems are the source for an even larger and more significant feature: a network of subglacial rivers on an almost unimaginable scale. What we are seeing is a fundamental rewriting of how an entire continent works, with consequences for every coastline on Earth. The science is moving incredibly fast, and if this kind of calm exploration into our world helps you unwind, consider liking the video and subscribing to the channel. Now, let's follow where the water from these pulsing lakes is going. If the subglacial lakes are the heart of Antarctica's hidden plumbing, then the rivers and canyons are its arteries. These are not small trickles. They are vast, organized river systems that channel enormous volumes of water from the middle of the ice sheet toward the ocean. Research has uncovered river systems hundreds of miles long, some carrying flows comparable to major surface rivers like the Thames in London. These rivers flow at the base of the ice, in the boundary between the ice and the rock below. The water is often at high pressure, trapped by the weight of the ice. As it flows, it doesn't just lubricate the ice, it carves channels and canyons into the base of the ice sheet itself. This thins the ice from the bottom up. But their most important function is as a delivery system. They create a direct path for lubricating water to travel from a geothermal hotspot or a draining lake all the way to the grounding line of the continent's largest glaciers. The grounding line is the critical point where a glacier leaves the land and begins to float on the ocean as an ice shelf. This is where the internal and external forces of collapse meet. There is no better example of this than the Thwaites Glacier in West Antarctica, a river of ice often called the Doomsday Glacier, for its potential impact on sea level rise. Thwaites alone holds enough ice to raise global sea levels by over 2 feet, but more importantly, it holds back much of the rest of the West Antarctic ice sheet. For years, we have known that Thwaites is being melted from below by warm ocean water. But recent research shows that subglacial rivers are making the situation more complex. Warm, salty ocean water is not just melting the front of the glacier. It is being drawn into the mouths of these subglacial channels at the grounding line. This warm ocean water is then carried, through this hidden river system, deep underneath the glacier. In 2019, an expedition discovered a huge cavity at the base of Thwaites, growing rapidly. This space was formed by warm ocean water being funneled deep under the glacier by the subglacial water system. More recent research, using an underwater robot named IceFin, found that while melting across broad areas was slower than some models predicted, the melting within cracks and channels was happening much more quickly. The water funnels heat into these weaknesses, widening them from the inside. This creates a feedback loop. The more the glacier melts, the more water can flow through the subglacial system. This enhanced flow can then transport even more warm ocean water inland, which in turn speeds up the melting. The hidden rivers are not just lubricating the glacier's slide into the sea. They are actively bringing the agent of their own destruction, warm ocean water, deep into the heart of the ice sheet. And now, thanks to new mapping of the seafloor, we know these pathways extend even further than we imagined. Extensive mapping efforts have revealed a vast network of submarine canyons carved into the seafloor around Antarctica. These canyons act as deep channels that can funnel that warm circumpolar deep water from the open ocean right up to the continent, and directly into the mouths of the subglacial river systems. The entire system appears to be connected. The story of Antarctica's internal collapse is not just about the present, it is also rooted in the past. To understand what might happen, scientists are drilling deep into the continent's memory, preserved in layers of ancient mud buried beneath the ice. And the story from Antarctica's past carries a quiet warning. An ambitious international project called SWAIS-2C is designed to find out what happened to the West Antarctic ice sheet during past warm periods. After multiple attempts, the team achieved a landmark success. At a remote site, after drilling through more than 500 meters of ice, they recovered a nearly 230-meter-long sediment core from the seabed below, the longest ever retrieved from beneath an ice sheet. This core is a time capsule. Each layer of mud tells a story about the environment when it was deposited. Preliminary dating suggests the record could span millions of years, including periods when global temperatures were higher than they are today, providing a direct analog for our future. Already, the core is yielding important clues. Within its layers, scientists have found the remains of marine organisms that need sunlight to survive. They have found sand layers that look like they came from a beach. The only way these could exist at this location, deep in the interior of the ice sheet, is if this area was once open ocean. This is direct physical evidence that during past warm periods, the West Antarctic ice sheet may have retreated dramatically, or even collapsed entirely. The timing of these events has always been uncertain, but this core provides a ground truth that can help anchor our models. Scientists can now analyze these layers to determine what ocean temperatures and CO2 levels were when these events occurred. Early indications from the SWAIS-2C project are deeply concerning. They suggest that the tipping point for the West Antarctic ice sheet may be close to the 2 degrees Celsius of global warming that world leaders are trying to avoid. It proves that this scenario has happened before. Much of the bedrock in West Antarctica lies far below sea level, making it inherently unstable. Once a large-scale retreat begins, driven by warm water at its base, it can become a runaway process. The sediment cores are a message from a past Earth, telling us that the systems we are currently pushing have changed before. The internal plumbing system we see today, the rivers and lakes, are operating on a landscape that has a history of instability. This historical precedent transforms the modern observations from merely interesting to truly significant. It suggests that the internal changes we are beginning to witness may be the reactivation of an ancient and powerful process. The internal plumbing of Antarctica, its geothermal heat, its pulsing lakes, its vast river systems, has existed for thousands of years, operating in a state of relative equilibrium. But today, this ancient, hidden world is meeting a new and powerful force: our changing climate. The external triggers of a warming world are now interacting with the internal mechanisms of collapse, creating a feedback loop that could push the entire system into a new state. The first and most important trigger is the warming ocean. Warm circumpolar deep water is not just melting the ice from the outside. It is the fuel being injected into the internal engine of collapse. At the grounding lines of glaciers like Thwaites, the subglacial river systems are not just sending fresh water out. They are also drawing warm, salty ocean water in, pulling it deep into the heart of the ice sheet. The internal and external systems are not separate, they are feeding each other. The second external trigger comes from the atmosphere and the sea ice on the ocean surface. In the winters of 2016 and 2017, a gigantic hole in the sea ice, known as Apollonia, opened up over an undersea mountain called Maud Rise. This opening vented a colossal amount of heat from the ocean into the cold polar atmosphere. Recent research suggests a combination of stronger winds and a more intense ocean current, both linked to broader climate shifts, drove a process that pushed warm deep water up to the surface. This warm water melted the sea ice from below, creating the hole. This event is a stark demonstration of how changes in the atmosphere and ocean can create large, localized heat events that disrupt the Antarctic system. These events can alter ocean circulation and lead to more warm water being pushed toward the continent, further intensifying the melt at the ice shelves and feeding the subglacial systems. We are learning that these frozen worlds are far more dynamic than we ever thought. They are not simple, solid blocks. They are complex, dynamic systems, full of hidden movement, and they are cracking, churning, and changing from the inside out. We began this journey with an image of Antarctica as a fortress under siege from the outside. We end it with a profoundly more complex and humbling picture. The fortress is not solid. It is filled with hidden arteries, warmed by the planet's own heat, and governed by a quiet pulse of filling and draining lakes. For thousands of years, this secret world lay in a delicate balance. But no longer. The warming oceans are not just lapping at the edges. They are being drawn into the heart of the continent through a network of hidden rivers, melting the ice from within. The atmosphere is creating heat events that disrupt the protective barrier of sea ice, further changing the system. The collapse of Antarctica is not a simple, linear story. It is a story of interconnected systems, where the external changes of our time are amplifying a hidden, internal vulnerability that has always been there. This is not a problem for a distant future. The pulse of the hidden lakes is being measured now. The flow of the secret rivers is quickening now. The meeting of these two worlds, the ancient, internal plumbing and the new, warmer climate, is happening right now. The question that remains is no longer if these systems will lead to significant sea level rise, but how quickly. We have looked beneath the ice and found a mechanism for change far more rapid and unpredictable than we once knew. The sleeping giant is stirring, and it is being changed, not just from the outside but from the inside out. The hidden destructive power in your ice cube. A road split open. A thick steel pipe, warped and torn. A mountain of solid granite, fractured and crumbling into shattered rock. This is not the aftermath of an industrial accident, but the work of a quiet, inexorable force we invite into our homes. A force we use to cool our drinks. This is what happens when we try to contain one of the most deceptively powerful phenomena on the planet. And it all begins with an ordinary ice cube. It floats, seemingly passive and inert. Yet inside this small, crystalline solid is a story of molecular arrangement, and of a fundamental peculiarity in the fabric of the universe's most essential compound. How can something so common, something we associate with stillness, possess the energy to pulverize steel and reshape the surface of our world? How can the simple act of freezing water unleash a pressure that rivals the deepest parts of the ocean? The answer is not about cold. It is about geometry. It is about an atomic arrangement so contrary to the laws that govern most other substances that it turns a simple phase change into an act of immense power. This is the story of a strange and unique property of the water molecule, and the quiet, destructive power it unleashes. If this kind of calm exploration into the hidden world of physics helps you unwind, consider liking the video and subscribing to the channel. We are dedicated to peeling back the layers of the ordinary to reveal the extraordinary science that governs our world. The gathering storm, a demonstration in contained chaos. To understand this force, we must witness its effects. We must try to do the one thing this force does not allow, to be contained. Imagine an experiment, a demonstration of the inevitable outcome when you trap water and attempt to freeze it. The plan is simple, the physics profound. We begin with a thick-walled, threaded steel container, designed to withstand immense internal pressure. It is, by any normal measure, incredibly strong. We fill it with ordinary water, completely full, ensuring there are no air pockets, no empty space for expansion. Then, we seal it with a heavy, threaded steel plug, wrenched tight. Once sealed, its fate is set. We place it into an environment of deep, sub-zero temperatures. And then, we wait. What we are waiting for is the pressure. The air pressure around you now is about 14.7 pounds per square inch, or psi. A car tire is inflated to around 35 psi. The pressure at the bottom of the Mariana Trench is about 16,000 psi. The force we are about to unleash inside this steel container can, in theory, reach over 30,000 psi. For a long time, scientists struggled to measure this force properly, with early experiments in heavy brass containers often failing unexpectedly. Compared to this force, the walls of a standard copper water pipe in a home are almost insignificant. As our steel vessel sits in the cold, a silent process begins, governed by molecular geometry. This is not just an experiment, it is a trap. To understand why it is destined to fail, we have to shrink down to the molecular level and witness the strange, microscopic arrangement that makes this happen. A dance of molecules, the science of the anomaly. Every story about water begins with the water molecule itself, H2O. One large oxygen atom is bonded to two smaller hydrogen atoms, forming a V shape at a specific angle of about 104.5 degrees. The oxygen atom is highly electronegative, meaning it pulls shared electrons closer to itself. This gives the oxygen side of the molecule a slight negative charge and the hydrogen side a slight positive charge. This imbalance makes water a polar molecule, a tiny magnet with a positive and a negative pole. This polarity is the key. In liquid water, these molecules are in constant, disorganized motion, tumbling and sliding past one another. The positive hydrogen end of one molecule is fleetingly attracted to the negative oxygen end of another, an attraction called a hydrogen bond. In liquid water, these bonds form and break in fractions of a second. This chaos allows the molecules to pack together quite tightly, which is what gives liquid water its density. But something remarkable happens as the temperature drops. The molecules slow down. Their frantic dance becomes less vigorous. As they slow, the hydrogen bonds last longer, becoming more stable. And then, at 0 degrees Celsius, the chaos stops. The water molecules no longer have enough energy to break their hydrogen bonds. Instead of a disorganized crowd, they lock into a highly ordered, rigid formation. This is the moment water becomes ice. Here, the anomaly reveals itself. In this frozen state, each water molecule forms exactly 4 stable hydrogen bonds with its neighbors. To achieve this, the molecules must arrange themselves into a specific, repeating pattern, a hexagonal crystal lattice. Think of it as a 3-dimensional honeycomb. And this is the crucial part. To build this open, hexagonal structure, the molecules must push each other apart. Unlike the crowded state of liquid water, the molecules in ice are held in a wide, organized formation. There is now a significant amount of empty space within the crystal structure. This locked-in, open lattice takes up more space than the disorganized liquid. This is the great anomaly of water. Almost every other substance becomes denser when it freezes. Water does the opposite. As it freezes, it expands by about 9%. Though scientists like René Descartes noted this expansion as early as the 17th century, it was later, through the work of physicists like William John Macquorn Rankine in the mid-1800s, that its thermodynamic principles began to be understood more deeply. Because of this 9% expansion, a given volume of ice is less dense than the same volume of liquid water. That is why ice floats. That is why an ice cube bobs at the top of your glass, and why massive icebergs drift in the ocean. But this elegant molecular structure holds a quiet power. That 9% expansion is not a suggestion, it is a demand. The water molecule, in its search for the stability of the ice crystal, will generate immense force to claim that extra space. And back in our thought experiment, inside our sealed steel container, that demand is about to be met with unyielding resistance. The inevitable failure. For hours, the steel vessel sits in the cold. Inside, as the first ice crystals form, the process begins. The hexagonal lattice starts to build, molecule by molecule. At first, the pressure barely rises. But water is famously incompressible. As more liquid turns to solid ice, the rigid crystal structure grows inward, demanding that extra 9% of space. The pressure begins to climb. First to 1000 psi. Then 5000 psi. The steel holds. The pressure continues its relentless rise. 10,000 psi. 15,000 psi. The hydrogen bonds continue to lock into place, an inexorable army assembling in the dark. 20,000 psi. The steel itself begins to strain. 25,000 psi. The force inside is now equivalent to placing a mid-sized car on an area the size of a postage stamp. And then, a catastrophic failure occurs. It does not start with a leak. With a sudden, sharp crack, the steel gives way. Perhaps the threads of the plug are stripped bare in an instant. Or a hairline fracture in the container wall, stressed beyond its limit, propagates in a millisecond, tearing the metal wide open. The result is a violent release of energy. The pressure that took hours to build is gone in a fraction of a second. We have witnessed that the formation of an ice cube is an active, expansive, and incredibly powerful process. Now that we understand what it can do in a contained setting, Let's explore where this hidden destructive power appears in the world around us. The ripple effect, from pipes to mountains. The failure of our steel vessel is an accelerated demonstration of a phenomenon that causes significant damage every year: bursting pipes. The actual mechanism is subtle. When a pipe is exposed to cold, ice begins to form, creating a solid plug. This plug itself rarely breaks the pipe. The problem is what happens next. The ice plug grows, acting like a piston, pushing the remaining, unfrozen water ahead of it. If that water is trapped by a closed faucet or valve, there is nowhere for it to go. You have an ice plug pushing forward, a closed valve holding fast, and a section of liquid water trapped between them. As the ice continues to expand, it relentlessly compresses this trapped water. Because water is nearly incompressible, the pressure skyrockets. It builds in the liquid section of the pipe until it finds the weakest point. It is not the ice that directly breaks the pipe, it is the immense hydraulic pressure of the trapped water. The pipe ruptures, ready to unleash a torrent as soon as the ice thaws. This same force operates on a geological timescale, shaping our planet through a process called frost wedging. It begins with a small crack in a rock. Rainwater seeps in. As temperatures drop, that water turns to ice. It expands by 9%, pushing against the walls of the crack, widening it slightly. When the weather warms, the ice melts, and water seeps deeper into the newly enlarged crack. The next time it freezes, the process repeats. This relentless freeze-thaw cycle, repeated over thousands of years, is a patient and persistent force. It can split massive boulders. On mountain faces, it pries loose huge chunks of rock, which tumble down to form the sloping piles of debris known as talus slopes. Much of the shattered appearance of the world's mountain ranges is a quiet testament to the power of frost wedging. This molecular quirk even creates beautiful, strange objects in our freezers. An ice cube with a sharp spike growing out of it is another manifestation of this expansion. It happens when the surface of the ice cube freezes over first, leaving a small pinhole. As the water underneath continues to freeze and expand, it squeezes the remaining liquid up through that hole. As this water emerges, it freezes in layers, building a hollow spike until all the water inside is frozen solid. It is a quiet piece of physical sculpture, created by the exact same pressure that shatters rock and bursts steel. Beyond Ice 1, a universe of frozen water. The hexagonal ice we know, the kind in our freezers, is technically known as ice IH. It is the stable form of ice on Earth's surface. But it is by no means the only kind. Under different conditions of pressure and temperature, water can arrange itself into a surprising array of different solid forms. As of today, scientists have identified around 20 different crystalline phases of ice. There's ice IC, with a cubic crystal structure, which can form in the upper atmosphere. Under immense pressure, water molecules can be forced into far denser arrangements, creating high-pressure forms of ice that are actually denser than liquid water. Some of these phases exist at conditions so extreme they challenge our intuition. Ice 7, for instance, can exist at room temperature or even hotter, but only under pressures tens of thousands of times greater than our atmosphere. This is a form of literal, hot ice, thought to exist on the ocean floor of distant moons like Europa, crushed under the weight of water and rock. This variety shows just how complex this simple molecule is. The flaw that causes water to expand is specific to the low-pressure conditions here on Earth. Yet this one property has had the single most profound consequence for the story of life. A paradoxical guardian, the flaw that enables life. We have focused on the destructive power of freezing water. But now we must perform a reversal, because this same flaw is perhaps the most important reason that complex life can exist in the freshwater bodies of our world. Imagine a thought experiment. What would happen if water behaved like most other substances, contracting when it froze? Consider a lake in late autumn. The air temperature drops. The surface water cools, becomes denser, and sinks. This is normal. But if water behaved normally, this process would continue. The water at 0 degrees Celsius would be the densest, so it would sink to the bottom of the lake and freeze there. The ice would form on the lake bed and build upwards. Over the winter, the lake would freeze solid, from the bottom to the top. Any fish, amphibian, or plant would be encased in a solid block of ice. Every winter would bring a mass extinction event. But that is not what happens. Thanks to water's strange anomaly, a remarkable, life-saving scenario unfolds. As the lake cools, the surface water cools and sinks. But this process stops at 4 degrees Celsius. This is the temperature at which liquid water is at its maximum density. As the surface water cools below *4 degrees Celsius, the anomaly begins. The water starts to expand slightly and becomes less dense. This layer of cold water, from 4 degrees Celsius down to 0 degrees Celsius, floats on the slightly warmer, denser water below. When the surface finally reaches 0 degrees Celsius, the ice that forms is even less dense, expanding by its full 9%. So it floats, creating a solid cap on the surface of the lake. This layer of ice is a salvation. It acts as an insulating blanket, protecting the liquid water below from the frigid air. Beneath this shield, a stable refuge exists. The densest water, at a relatively mild 4 degrees Celsius, settles to the bottom, providing a safe haven for fish and other creatures. They all owe their existence to this strange, counterintuitive property. The destructive power in an ice cube is also the guardian of life. So we return to where we started. An ice cube, clinking in a glass. It is no longer so simple. We have seen its alter ego. A capacity for brute force, the power to rupture hardened steel. We have traced that power back to a specific angle in a tiny molecule. We have watched this force sculpt our planet, breaking down mountains with patient, relentless cycles. And then, in the final, most important reversal, we have seen that this destructive flaw is also a creative one. The same property that is a menace to our plumbing provides a life-saving sanctuary in our lakes and rivers. The expansion that bursts a pipe also lays down the insulating blanket that allows an entire ecosystem to survive the winter. The story of the ice cube is a paradox. It is a story of destruction and preservation, of a molecular flaw that is also a perfect design. It is a quiet reminder that the most profound and world-shaping forces are often not the loud and the obvious, but the ones we take for granted. The universe is full of these secrets, waiting in plain sight. All we have to do is look a little closer, and ask why. An ice shelf the size of a state disappeared in 35 days. In the first days of 2002, scientists began watching a vast Antarctic ice shelf, a feature of our planet that had been stable for over 12,000 years. 35 days later, it was gone. An area of ice the size of Rhode Island, over 700 feet thick, had broken into countless pieces. This wasn't a slow melt. It was a quiet, rapid disintegration, broadcast from the still vantage of space by satellites. Researchers could only watch as a frozen giant, a permanent fixture on the map, turned into open ocean in just over a month. This is the story of that collapse, a chain of events that exposed a hidden world, unleashed rivers of ice, and offered a quiet preview of a process that is still happening today. Before the collapse, there was a calm. A deep, ancient, and deceptive calm. To understand what was lost, you must first understand what it was. The Larsen ice shelf was not just a piece of ice. It was a presence, a sprawling, seemingly eternal extension of the Antarctic continent itself, stretching along the eastern coast of the Antarctic Peninsula like a great white shield. For mapmakers, it was a solid line. For the planet, it was a critical piece of a much larger system. The section that would vanish was known as Larsen B. It was one part of a larger complex named after the Norwegian whaler Carl Anton Larsen, who first navigated its edge in 1893. By the start of the 21st century, the Larsen complex was already showing signs of change. The northernmost section, Larsen A, had shattered and collapsed back in January of 1995. It was a surprising event, a quiet warning. But Larsen B was different. It was larger, thicker, and believed to be far more resilient. It covered 3,250 square kilometers, an area comparable to the nation of Luxembourg. Its ice was, on average, 220 meters thick. That's over 720 feet. Imagine a skyscraper lying on its side, floating on the ocean, and you begin to get a sense of the scale. And this was not a temporary winter freeze. Scientific evidence, gathered from sediments on the seabed after the collapse, would later prove that the main body of the Larsen B ice shelf had been in place for the entire Holocene period. For at least 12,000 years, since the end of the last great ice age, it had been a constant. Empires rose and fell, civilizations flourished and vanished, the entire history of human agriculture and industry had played out, and all the while, the Larsen B had remained. It was, by any human measure, permanent. But the most important role of an ice shelf is not defined by its size or its age, but by its function. An ice shelf is a buttress, a gatekeeper, a cork in a very large, very cold bottle. Think of it this way. Antarctica is covered in ice, and this ice is not static. Gravity is always pulling it towards the sea in slow-moving rivers of ice called glaciers. When these glaciers reach the coast, they flow out onto the ocean, and this floating extension is what forms an ice shelf. This floating shelf acts as a break. Its immense bulk, pinned against islands and the sides of its own bay, creates a force of back pressure that physically holds back the glaciers on land. This is a point of critical importance. The melting of a floating ice shelf, as dramatic as it sounds, does not, in itself, significantly raise global sea levels. Like an ice cube in a glass of water, it is already displacing its own volume. The real danger comes from what happens after the shelf is gone. When you remove the buttress, the glaciers behind it are released. The cork is popped, and the contents of the bottle begin to pour into the ocean at a new speed. And the world that the Larsen B inhabited was changing. The Antarctic Peninsula, that long finger of land pointing towards South America, had become one of the most rapidly warming regions on Earth. Since the late 1940s, average temperatures there had climbed steadily. This wasn't a gentle warming, it was a fundamental shift in the environment. The collapse of Larsen A in 1995 was the first sign of this new reality. After its demise, scientists at the British Antarctic Survey began to watch its larger neighbor, Larsen B, with a growing sense of concern. In 1998, they ran the models. They saw the warming trends and made a prediction. If the warming continued, Larsen B would likely enter a phase of irreversible collapse. David Vaughan, a glaciologist with the survey, was one of those scientists. They watched as the shelf began to retreat over the next few years. They knew its end was coming. But as Vaughan would later say, we knew what was left would collapse eventually, but the speed of it is staggering. Hard to believe that 500 billion tons of ice sheet has disintegrated in less than a month. The diagnosis was correct, but no one was prepared for the sheer swiftness of the end. A 12,000-year-old body of ice does not simply give up. It must be broken. The collapse of the Larsen B was the culmination of a long, quiet process, driven by warm air from above and a warming ocean from below. This two-sided change exploited a flaw hidden within the ice itself, turning its own structure against it. The first front was the atmosphere. As the Antarctic Peninsula heated up, summer melting increased dramatically. For years leading up to 2002, the summers had been getting successively warmer. The summer of 2002, in particular, was exceptionally warm. For the first time in millennia, large quantities of snow and ice on the shelf's surface melted completely, forming vast, sapphire blue lakes. From space, These melt ponds were eerily beautiful, like blue jewels scattered across the white ice. To a glaciologist, however, they were a sign of a process known as hydrofracturing. The physics are simple, but their effect was profound. Water is about 10% denser than ice. When meltwater pools on the surface, it finds its way into small, pre-existing cracks. As the lakes grow deeper, the weight of the water begins to exert immense pressure. It acts like a liquid wedge, driving the fracture deeper into the ice. A little water deepens the crack, which allows more water to pour in, which increases the pressure further. It's a feedback loop. The very substance that formed the ice shelf, water, was now the agent of its undoing. The incredible thickness of the Larsen B, its 720-foot wall of ice, became a liability. Scientists confirmed that this process was powerful enough to drive fractures clean through the entire thickness of the shelf, from the surface to the ocean below. While this was happening from above, a second, more subtle change was happening from below. The waters of the Weddell Sea were also warming. Ocean currents, carrying slightly warmer water, were coming into contact with the underside of the floating ice shelf. This process, called basal melting, is invisible from the surface, a silent thinning from beneath. Year after year, this warmer water was compromising the shelf's structural integrity. The foundation was being quietly eroded at the same time the surface was being wedged apart. The final piece of the puzzle lay in the ice's own internal structure. An ice shelf is not a uniform block. It is a complex landscape of stresses and strains. For centuries, these flaws had been stable. But under the combined effect of surface melt and basal thinning, they began to grow. In the final years, the process accelerated. Rifts began to link up, forming a continuous path of failure. The internal skeleton of the ice was being broken. The stresses were no longer distributed across a solid mass. They were being concentrated at the tips of these growing fractures. The shelf was becoming structurally unsound, primed for failure. The warm summer of 2002 was not the cause of the collapse. It was, as Ted Scambos, a senior research scientist at the National Snow and Ice Data Center, put it, the final straw. The Larsen B was a weakened giant, thinned from below, fractured from above, and internally broken. It was just waiting for the final push. The end began on January 31, 2002. It wasn't marked by a single event, but by a subtle change visible only from space. On the satellite imagery that day, the network of sapphire blue melt ponds had reached its maximum extent. The shelf was waterlogged. At research centers around the world, glaciologists like Ted Scambos watched their screens with a mixture of scientific fascination and a profound sense of awe. They were about to witness the death of a geological feature, an event on a scale no human had seen before. The first 10 days of February were a period of rapid escalation. The web of cracks, supercharged by the weight of the meltwater, began to give way. Satellite passes revealed long, thin icebergs, like giant splinters, starting to break away from the northern edge. The process had entered an accelerated phase. The connections that held the front of the shelf together were failing. By February 17, the disintegration was undeniable. The main front of the ice shelf had retreated by more than 10 kilometers, over 6 miles. The images from February 23 showed an even more chaotic scene. The scientists watching realized they were no longer observing a retreat, but a complete fragmentation. The network of rifts had finally connected. The integrity of the shelf was gone. It was no longer a single object, but a loose collection of enormous ice blocks. The climax arrived in the last days of February and the first week of March. Between February 23 and March 7, the process became a cascading failure. The shelf didn't melt, it shattered. In this short period, the main body of the Larsen B, a solid feature for 12,000 years, disintegrated into thousands of sliver-like icebergs and a vast mixture of ice and water. The statistics are almost difficult to comprehend. 3,250 square kilometers of ice, gone in 35 days. Over 500 billion metric tons of ice cast into the ocean. In Argentina, glaciologist Pedro Scavarca realized from local data that something profound was happening and quickly mobilized an aircraft to get photographs, confirming the satellite data with his own eyes. Meanwhile, the British Antarctic Survey's research ship, the RRS James Clark Ross, happened to be in the region and was carefully diverted. Its crew began navigating through what they described as an armada of icebergs to collect samples from the heart of the collapse zone. They were capturing data from a scene that was still unfolding. The satellite images from this final week are among the most dramatic ever captured of our changing planet. Where there was once a seamless white plain, there was now a jumble of floating debris. Many of the new icebergs were too tall and thin to float upright. One by one, they toppled over, spreading out across the bay. One scientist likened it to a neat row of books being knocked off a shelf. As these massive blocks of ice capsized, they revealed a stunning sight. The underside of the ice shelf, which had been in darkness for millennia, was exposed to the sun. This ice was incredibly pure and dense, and it reflected light with an intense, otherworldly sapphire blue. The bay was filled with these brilliantly blue icebergs, the last vestige of ancient ice from the deep. The sound would have been a continuous, grinding roar, a sound that likely continued for days on end. By March 7, 2002, the main event was over. The great ice shelf was gone. In its place lay open water, choked with countless icebergs. Scientists who had predicted its demise were still left stunned by the sheer velocity of the event. They had witnessed the near-instantaneous removal of a major geographic feature. The Titan was gone, and in its place, a host of new, urgent questions had appeared. The collapse was over, but the consequences were just beginning. The disappearance of the Larsen B was the inciting incident for a new, and in many ways more revealing, chapter. The immediate aftermath revealed a profoundly altered landscape and gave humanity a fleeting glimpse into a world hidden since the dawn of history. The first and most immediate consequence was the release of the glaciers. With the buttressing force of the ice shelf gone, the glaciers it had held in check began to move forward. Scientists used satellite radar data to track their speed, and what they found was astonishing. 4 major glaciers that had fed into the Larsen B, Hectoria, Green, Evans, and Joram, began to accelerate dramatically. At its peak, the lower part of the Hectoria glacier accelerated by as much as 8-fold. To put that into perspective, NASA scientists offered an analogy. It was like a car suddenly accelerating from 55 miles per hour to 440 miles per hour. The river of ice had become a torrent. This was land-based ice, previously held in reserve, now being added to the ocean at a wildly accelerated rate. The gatekeeper was gone, and the gates were wide open. But the collapse did more than just release ice. It revealed a secret. For 12,000 years, the seafloor beneath the Larsen B had been locked in darkness, an ecosystem isolated from the sun. Its sudden removal was, for biologists, an unprecedented natural experiment. Scientists from around the world raced to the site. They knew they had a small window to study this pristine world before it was changed forever. What they found was like something from another planet, a world not driven by photosynthesis, but by chemosynthesis. They discovered communities of organisms clustered around cold seeps, where methane provided the energy for life. This was a unique, isolated ecosystem adapted to perpetual darkness. With the ice gone, sunlight now penetrated the water for the first time in millennia. Within just a few years, scientists watched as phytoplankton, the microscopic plants at the base of most marine food webs, began to bloom. A new ecosystem was being born, right on top of the old one. They were witnessing a complete ecological transition in real time, A moment of scientific wonder in the midst of a climate disaster. The story of Larsen B is a quiet illustration of how quickly our world can change. It shows that systems we think of as permanent can be surprisingly fragile, and the consequences of pushing them too far can be sudden and profound. If you find these deep dives into the story of our planet helpful, consider subscribing to the channel. Learning about these events is the first step, and there are many more stories like this to tell. Your support helps bring this information to light. Today, more than 2 decades later, the story of the Larsen B is still not over. A small southern portion of the original shelf, now known as the Scar Inlet Ice Shelf, survived the 2002 event. But it is a ghost of its former self. A 2015 NASA study concluded that this remnant is weakening and riddled with cracks. Ted Scambos described it as having huge cracks everywhere now, stating that it's on the brink of its own breakup. Its disintegration seems not a matter of if, but when. It's the long, slow-motion epilogue to the events of 2002. The true legacy of the Larsen B, however, extends far beyond its own bay. Its collapse was a paradigm shift for climate science. It proved that ice shelves could fail with a speed no one had previously thought possible. It validated the sobering theory of hydrofracturing and showed the world how a warming atmosphere could shatter a polar giant. The event was, in essence, a message. All eyes have now turned to the remaining, even larger ice shelves of Antarctica. The Larsen C, to the south, calved one of the largest icebergs ever recorded in 2017. And further south lie the true titans, the Ross and Ron ice shelves. Each is nearly the size of Spain. They act as the buttress for the colossal glaciers of the West Antarctic ice sheet, which hold enough ice to raise global sea levels by many meters. The what-if scenario that concerns glaciologists is simple. What if the same combination of warm air and warm ocean that took Larsen B begins to take hold there? The collapse of the Larsen B ice shelf was not an isolated incident. It was a demonstration of physics, a lesson in consequences. It showed us that the great ice sheets are not just slowly melting, they are capable of structural, catastrophic failure on a human timescale. As scientist Ted Scambos summarized it, this problem of sea level rise is a real one. It's likely to happen, and the steps could proceed more rapidly than we thought. The 35 days in 2002 were not the end of a story. They were the quiet opening scene of a much larger one, a story that is still unfolding, and in which we all have a part to play. How pressure makes glaciers flow like butter. We see them in photographs, vast and silent. Rivers of ice, moving on a scale that is difficult to comprehend, grinding slowly toward the sea. We are told that they are melting, and this is true. We are warned that their end will change the maps of our world, and this is also true. But this story, of a simple change from solid to liquid, driven by a warming planet, is only part of the picture. The full story is quieter, and in some ways, more profound. It is a story that begins not with the sun's warmth, but with the immense, steady weight of the glacier itself. The most important secret behind why this solid river of ice moves isn't just about heat. It's about pressure. A pressure so great that it quietly rewrites the rules of physics. It is a pressure that encourages solid ice, deep within the glacier, to do something that feels impossible, to behave like a liquid. Imagine a block of solid ice. It is hard and unyielding. Now, imagine this block of ice is not in a freezer, but is the size of a mountain. A mountain of ice thousands of feet thick, weighing billions of tons. What happens at the very bottom of that mountain? It is not just cold. It is under a pressure so extreme that it allows for an unexpected effect. The ice can begin to melt, not from heat alone, but from the force squeezing it. This is the hidden engine driving nearly every major glacier on the planet. In this video, we'll journey from the quiet physics of a single water molecule to the movement of continental ice sheets, to uncover how pressure, not just temperature, allows a glacier to flow like butter. The strange case of water, a molecule unlike any other. To understand how a mountain of solid ice can flow, we have to shrink our perspective down to the molecular level. We need to talk about water. It is perhaps the most familiar substance on Earth, yet it is one of the most unusual. Almost every other substance, from iron to carbon dioxide, follows a simple rule. When it turns from a liquid to a solid, its molecules pack together more tightly. The solid form is denser. A solid piece of almost anything else, dropped into its own liquid, would sink. But not water. Water is a quiet exception. When liquid water cools, it does become denser, but only to a point. At 4 degrees Celsius, it reaches its maximum density. Then, as it cools toward freezing, something else begins to happen. The H2O molecules, instead of packing tighter, start to arrange themselves into a highly organized, open, crystalline structure. The bonds between them push them slightly apart into a fixed, hexagonal pattern. The result is that ice is about 9% less dense than liquid water. This is why ice floats. It is why lakes freeze from the top down, creating an insulating layer that allows life to survive below. This one, simple property is a cornerstone of life on Earth. And it is the key to understanding the movement of glaciers. Because this less dense solid structure is vulnerable. It's a structure that nature, under the right conditions, can change. The relationship between a substance's temperature, pressure, and its state is shown on what scientists call a phase diagram. For most substances, the line separating solid and liquid slopes forward. This means as you increase pressure, you need a higher temperature to melt it. You are squeezing the molecules together, reinforcing their solid structure. But for water, that line slopes backward. This is a direct result of ice being less dense. What this backward sloping line tells us is something fundamental. If you take ice and increase the pressure on it, you actually lower its melting point. You are encouraging it to become a liquid. The universe, in a sense, finds the spread out structure of ice to be inefficient. When you apply immense pressure, you are physically pushing the H2O molecules to abandon their open crystalline lattice and collapse into the denser liquid form. You are helping them melt. For every additional atmosphere of pressure, the melting point of ice drops by about 0.0075 degrees Celsius. This may not seem like much. But at the bottom of a glacier, the pressures are not just a few atmospheres, they are hundreds. And this small, strange quirk of water is what allows continents of ice to flow. Before we scale up, let's see this principle in a more familiar setting. The skater's secret glide. Think of an ice skater. A figure skater tracing a quiet spiral, or a hockey player making a sharp turn. What is happening in that impossibly thin space between the steel blade and the frozen surface? For a long time, the explanation was simple friction. The blade generates heat, which melts a thin layer of water, creating a lubricant. And while friction is part of the story, it isn't the whole picture. The real process involves pressure, in a phenomenon known as regelation. Regelation is the melting of ice under pressure, and its refreezing once that pressure is released. Imagine the skater's entire weight, focused onto the razor-thin edge of a skate blade. The surface area is so small that the pressure on the ice directly beneath it becomes enormous, thousands of times greater than normal atmospheric pressure. This immense pressure does exactly what water's phase diagram predicts. It lowers the melting point of the ice directly under the blade. Even if the rink is a few degrees below zero, the pressure from the skate might lower the melting point to be even colder. The solid ice suddenly finds itself above its new, pressure-depressed melting point. And so, it melts. A microscopic, moving film of liquid water forms right under the blade, acting as a perfect lubricant. The skater does not glide on ice. They glide on this self-generated layer of water. As the blade moves on, the pressure is released from the ice it just left. The melting point instantly returns to normal, and the water refreezes, healing the track behind the skater. This entire cycle, pressure, melt, glide, release, refreeze, is regelation. It happens quietly, a continuous wave of melting and freezing traveling with the skater. It is why skating feels so smooth. It's also why skating becomes difficult if the ice is extremely cold. If the ice is at -30 degrees Celsius, for example, the pressure from the blade might not be enough to lower the melting point sufficiently to create that water layer. The blade scrapes, but it does not glide. This small-scale example is the perfect entry point. We have seen that pressure can help turn solid ice into a liquid. Now, let's take this principle and apply it to an even more dramatic demonstration. Slicing solid ice with a wire. There is a classic physics demonstration that illustrates the power of regelation. It is simple, yet it reveals something fundamental. Imagine a large, solid block of ice resting on a support. You take a thin metal wire and loop it over the top. From each end of the wire, you hang a heavy weight. At first, nothing seems to happen. But if you watch patiently, you will see the wire begin to sink into the ice. Slowly, steadily, it cuts its way down through the solid block. The pressure exerted by the thin wire, due to the weights, is immense. Just like the ice skate, this pressure lowers the melting point of the ice directly beneath the wire. A thin film of water forms, allowing the wire to slip downwards. But here is the remarkable part. As the wire sinks, the water that was just melted above it is no longer under pressure. Its melting point returns to normal, and it instantly refreezes. The wire continues its path, leaving a trail of solid, refrozen ice in its wake. After some time, the wire passes completely through the block and falls away. And the block of ice is still there, completely solid. It has not been split. The wire has passed through it, melting its path ahead and sealing the path behind. This is the power of regelation in its purest form. It is a tangible demonstration that you don't need an external source of heat to melt ice. All you need is force. Now, we are ready to scale up. Forget a wire with a few kilograms of weight. Let's start thinking about the weight of a mountain. Building a river of ice. Before a glacier can flow, it must first be born. Its birth is a story of slow transformation, of time, and of accumulation. Glaciers are not simply frozen rivers. They are built, snowflake by snowflake, over centuries. It begins high in the mountains or in the polar regions, in a place called the accumulation zone. This is an area where more snow falls in winter than melts in summer. Each snowfall adds a new, fluffy layer, which at first is mostly air. As new layers pile on, the weight begins to press down. The delicate points of the snowflakes break and compress. The snow becomes granular. As years turn into decades, the pressure increases, squeezing the grains together, forcing the air out. This dense, granular stage, no longer snow but not yet ice, is called firn. The process continues. As hundreds of feet of new snow and firn accumulate, the pressure on the deepest layers becomes immense. The firn grains are compacted so tightly that they fuse together, recrystallizing into a solid mass of ice. The last remaining air bubbles are trapped inside, becoming tiny, pressurized pockets. These ancient bubbles are like time capsules, preserving samples of Earth's past atmosphere. When the ice reaches a critical thickness, typically around 50 to 60 meters, something changes. It is no longer a static pile of snow. The pressure at its base has become so great that the ice can no longer behave as a rigid solid. The bonds between the ice crystals are overwhelmed. The mass begins to deform and move under its own weight. It has become a glacier. A slow, moving river of ice. Think about the scale. A small alpine glacier might be a few hundred feet thick. The ice sheets of Greenland and Antarctica are more than 2 miles, or over 3 kilometers, thick at their centers. The weight is almost unimaginable. This is the force we are now dealing with. The crushing weight of eons. Let's try to put the pressure at the bottom of a glacier into perspective. A cubic meter of ice weighs just under a ton. A column of ice 1 kilometer thick exerts a pressure of around 90 atmospheres. At the thickest parts of the Antarctic ice sheet, the pressure can exceed 360 atmospheres. This is the force that brings the strange physics of water to life on a planetary scale. We've established that as pressure increases, the melting point of ice decreases. A pressure of 90 atmospheres lowers the melting point by about 2/3 of a degree Celsius. Under enough pressure, the melting point can drop to as low as -22 degrees Celsius. Now, consider the ground beneath the glacier. The Earth itself radiates a small but constant amount of geothermal heat. It is not a lot, but over the vast area of a glacier's bed, it is a steady source of thermal energy. So, at the base of a thick glacier, we have a convergence of factors. 1. Immense pressure from the weight of the ice. 2. This pressure lowering the melting point of the ice to below zero. 3. A gentle, constant supply of heat from the Earth below. The stage is set. The ice at the very bottom of the glacier, which might be at a temperature of -1 or -2 degrees Celsius, finds itself in an unusual situation. Due to the immense pressure, its melting point has been pushed down to be even colder than it actually is. It is, in effect, too warm to remain solid. And so, just as we saw with the skater and the wire, it is able to melt. This isn't a sudden event. It's a slow, steady process that creates a thin, persistent film of water at the interface between the glacier and the rock it rests upon. This film might only be millimeters thick, but its existence changes everything. It is the secret ingredient. It is the butter. The butter layer, basal sliding explained. This movement of a glacier over a lubricating layer of meltwater is called basal sliding. It is one of the two primary ways that glaciers move, and it is by far the fastest. The entire, colossal mass of the glacier is no longer frozen to the ground. It has become decoupled, separated from the bedrock by this liquid lubricant. With the friction between the ice and ground reduced, the fundamental force of gravity can take over. A glacier is almost always on a slope, however gentle. Once lubricated, this slight incline is all it needs. The entire ice mass begins to slide downhill, slowly but unstoppably. The amount of this basal water is the primary control for the glacier's speed. More water means less friction and faster sliding. This creates a complex plumbing system at the base of the glacier, a hidden world of channels and even vast subglacial lakes that scientists are just beginning to map. Recent observations have shown the surface of the Antarctic ice sheet rising and falling, suggesting massive amounts of liquid water moving beneath it, lubricating the ice as it flows. The ground beneath the glacier also plays a role. If the glacier rests on hard bedrock, the water allows it to slide. But if it rests on soft sediment, this sediment can become saturated with water, deforming and acting like a second layer of lubrication, further accelerating the glacier. This brings us to a useful distinction: temperate glaciers versus polar glaciers. Temperate glaciers, or warm-based glaciers, are found in places like the Alps or the Rockies. Their ice is at or near the pressure melting point throughout. These are the glaciers where basal sliding is the dominant form of movement. They are dynamic and fast-moving. Polar glaciers, or cold-based glaciers, are found in the extremely cold regions of Antarctica and Greenland. Here, the ice is so far below freezing that even the immense pressure at the base may not be enough to reach the melting point. The bottom of the glacier is frozen to the bedrock. These glaciers cannot slide easily. Their movement is much slower, and it comes from a completely different, quieter mechanism. So, we've just uncovered the biggest secret to how glaciers move fast: a hidden layer of water, created by a combination of pressure and heat. It's a concept that changes how we view these frozen giants. If this kind of calm exploration into the world helps you unwind, consider liking the video and subscribing to the channel. Now, let's get back to the ice, because sliding is only half the story. The slow creep, internal deformation. What about those cold-based glaciers frozen to the ground? Or the ice within a temperate glacier, above the basal layer? How does that move? The answer lies in the second mechanism of glacial motion, internal deformation, also known as plastic flow. We think of ice as brittle. If you hit an ice cube, it shatters. This is true for the upper part of a glacier, the top 50 meters or so, known as the zone of brittle flow. This ice is not under enough pressure to flow, so as the glacier moves, this upper layer cracks. But deep within the glacier, the story is different. Here, under immense, sustained pressure, the solid ice crystals themselves begin to deform. A glacier is a composite of billions of individual ice crystals. Under pressure, these crystals can stretch, bend, and slide past one another without the ice as a whole breaking. The best analogy is a deck of cards. If you push the deck from the top, the whole deck moves by individual cards sliding past each other. This is what happens inside a glacier. Layers of ice crystals slide over each other, allowing the entire mass to slowly flow downhill. This plastic flow is not uniform. It is slowest at the bottom and along the valley walls, where there is friction against rock. The velocity gradually increases toward the center and the surface. So, even in a glacier frozen to its bed, the surface is still moving forward, carried by the slow, creeping deformation of the ice below. This internal deformation is a much slower process than basal sliding. Glaciers that move this way might only advance a few centimeters a day. A fast-moving, sliding glacier can move many meters in a single day. In reality, most glaciers move through a combination of both. They slide over their beds on a film of meltwater, while at the same time, the ice within them is deforming and flowing. The total movement we see is the sum of both processes. Understanding the interplay between them is the core of modern glaciology. The scars of movement, crevasses and surges. The relentless movement of glaciers leaves marks on the ice itself. The most famous of these are crevasses. Crevasses are the deep cracks that form in the upper, brittle layer of a glacier. They are the visible expression of the stresses within the moving ice. As a glacier flows over an uneven landscape, it is forced to speed up, slow down, and bend. The plastic ice deep below can stretch to accommodate this. But the rigid surface ice cannot. It is pulled apart, and it cracks. For example, where a glacier flows over a steeper section, it speeds up, creating a series of parallel cracks. Crevasses rarely extend deeper than about 45 meters, because below that depth, the pressure is so great that the ice flows plastically, closing any cracks that might form. While crevasses are a constant feature, sometimes a glacier's movement can become unstable, leading to a glacial surge. A surge is a period of exceptionally rapid movement, where a glacier can suddenly accelerate, advancing tens or hundreds of times its normal speed. The leading theory for these surges relates back to our butter layer. They are thought to be caused by a failure of the subglacial plumbing system. Water can become trapped at the base, increasing pressure, lifting the glacier slightly, and dramatically reducing friction. The glacier then lurches forward. This is a powerful reminder of how critical that thin layer of water is to the stability of these ice masses. The sculptor of worlds. The power of a glacier, unlocked by pressure, is in its ability to transform the face of the planet. For millions of years, during successive ice ages, vast ice sheets and glaciers have acted as the world's most formidable sculptors. As a glacier slides, it carries with it an enormous amount of rock and debris. Rocks, from fine powder to massive boulders, become frozen into the basal ice, turning the bottom of the glacier into a gigantic sheet of sandpaper. This process, called abrasion, grinds away at the bedrock, smoothing surfaces and carving long striations that mark the direction of flow. In a process called plucking, meltwater seeps into cracks in the bedrock. This water then refreezes, expanding and breaking off chunks of rock, which are then carried away by the moving ice. Over thousands of years, this combination of abrasion and plucking carves out distinctive landscapes. Sharp, V-shaped river valleys are transformed into broad, U-shaped glacial valleys. The heads of valleys are excavated into deep, bowl-shaped amphitheaters called cirques. Where multiple cirques erode back to back, they create knife-edge ridges called arêtes and pointed peaks like the Matterhorn. The Great Lakes of North America were scoured out of weaker bedrock by this same immense power. When the glaciers retreat, they leave behind this transformed landscape, along with vast deposits of rock and sediment called moraines. Glaciers are not just features on the landscape, they are its architects. The climate connection, a system unbalanced. We began by challenging the simple idea that glaciers are moving just because they are melting from the top. We've discovered the hidden engine of pressure and the lubricating power of basal water. Now, we must bring the two stories together, because in our modern world, the story of heat and the story of pressure have become intertwined. Climate change is accelerating glacial movement through a series of feedback loops. First, warmer air increases melting on the glacier's surface. This meltwater doesn't just run off. It finds its way down through crevasses and vertical shafts called moulins, all the way to the glacier's bed. This provides a massive extra injection of lubricant to the basal sliding system. It supplements the water being created by pressure and geothermal heat, further reducing friction and accelerating the glacier's slide. More heat means more surface melt, which means more lubrication, which means faster flow. Second, and perhaps more critical, is the role of warming oceans. Many of the world's largest glaciers terminate in the ocean. As ocean temperatures rise, this warmer water eats away at the glacier's edge from below. It lubricates the point where the glacier lifts off the bedrock, known as the grounding line. By thinning the ice from below and reducing friction at this critical point, the warmer ocean allows the entire glacier to flow faster. It is like putting a car on a steeper ramp. The flow of ice into the ocean accelerates, which in turn thins the glacier further upstream, encouraging even faster flow. This is the scenario that concerns glaciologists. The mechanisms of pressure-driven flow are being supercharged. Glaciers are in retreat, not just because their surfaces are melting, but because their fundamental flow is being altered. The butter layer is becoming thicker and more widespread. Recent research has even shown that standard equations for glacier flow might need to be revised, as some ice deforms more readily than we thought, a finding that could change projections for the future. The story of how a glacier moves is more profound than simple melting. It begins with the unique physics of the water molecule, which decrees that solid ice is less dense than its liquid form. This simple fact creates a vulnerability. When subjected to the unimaginable weight of its own mass, the ice at the base of a glacier is able to exploit this. The pressure lowers its melting point, and with a small amount of heat, it melts, creating a secret, slippery layer that allows these masses of ice to slide across the land. This process, combined with the slow internal creep of the ice, is what turns a static pile of snow into a dynamic river. It is a force powerful enough to sculpt mountains and define the face of our planet. We have seen this principle at work in the elegant glide of an ice skater and the quiet passage of a wire through a block of ice, a phenomenon called regelation. But today, this ancient process has been placed in a new context. The heat we are adding to our atmosphere and oceans is amplifying these mechanisms, creating feedback loops that accelerate the flow of ice into the sea. The story of pressure and the story of heat have merged. The glaciers are not just melting away, they are sliding away. Understanding that a glacier flows like butter is no longer just a fascinating piece of physics. It is now a critical part of understanding the future of our planet. What part of this journey into the physics of ice felt the most surprising to you? Was it the idea of ice melting under pressure, or the sheer scale of the forces involved? Feel free to share your thoughts in the comments below. And if you want to keep exploring the quiet forces that shape our world, consider subscribing and joining us for our next video. The bizarre secret your freezer is hiding. It is a quiet experience, familiar in kitchens everywhere. You reach into your freezer for a few cubes of ice, only to find they have joined together, forming a single, solid mass that resists being separated. You might tap it on the counter, or run it under water. But this is not just an inconvenience. It is a clue. It is the first quiet signal that the ice in your freezer is hiding a deeper story. Because that simple act of sticking together is a doorway into a strange and beautiful world of physics. It is a journey that begins in your kitchen, and ends by revealing that this humble, frozen water is just one of at least 20 distinct types of ice known to science, some of which can exist at temperatures that rival the surface of the sun. What follows will change how you see a simple glass of water. We think we know ice. We think it is simple, solid, cold. But the truth is, water is one of the most mysterious and versatile substances in the cosmos. Its solid form is not one thing, but a family of crystalline structures, each with its own rules, its own form, and its own secrets. And it all begins with that stubborn clump of ice in your freezer. The kitchen counter conundrum. So, why do ice cubes stick together? The answer has a deceptively simple name: sintering. But the process itself is quietly elegant. The surface of an ice cube, even one in a freezer well below zero, is not a static, perfectly frozen wall. The molecules at the very edge exist in a constant state of motion. They vibrate with thermal energy. Unlike the molecules deeper inside, locked in place by their neighbors, these surface molecules have a certain freedom. A few of them will always have just enough energy to break away from the rigid crystal, existing in a strange, in-between state, not quite solid, not quite liquid. This is sometimes called a quasi-liquid layer. Imagine a perfectly ordered crystal, still and silent. The individuals in the middle are held firmly in place. But those at the very edge can move. They are still part of the structure, but they are less constrained. When two ice cubes are brought close to each other, these two restless, quasi-liquid layers touch. Suddenly, the water molecules in this new, shared layer find themselves trapped between two large, cold, and highly organized crystal structures. For a water molecule, joining a stable crystal is a much lower energy state. It is more comfortable. So, the molecules in that liquid bridge do not remain liquid. They align themselves with the crystal lattices of the cubes they're touching. They freeze. And in doing so, they form a solid bridge of new ice, welding the two cubes together. You can feel this happen. If you take two ice cubes from a cold freezer and press them together for a moment, they will fuse. The pressure creates a thin layer of water, and the deep cold of the cube's interiors quickly draws the heat out, refreezing it into a bond. This process is most effective when the ice is very cold, because a greater temperature difference drives the refreezing. If you let ice cubes warm up to exactly 0 degrees Celsius in a glass of water, you will find they no longer stick together. There is no longer a cold reservoir to pull the heat away. This same principle is behind another quiet kitchen event: the crackling sound an ice cube makes when you drop it into a drink. This is a phenomenon known as thermal shock. Your freezer keeps ice near -18 degrees Celsius. When that cold cube is dropped into a warmer liquid, its outer surface warms and tries to expand almost instantly. But the inside of the cube remains cold and contracted. This immense stress between the outer and inner layers is released in a series of tiny fractures, creating that gentle, crackling sound. This restlessness, this quiet tension between order and disorder at the surface of ice, is fundamental. The molecules are always trying to find the most stable arrangement. In your freezer, that means smoothing surfaces and bridging gaps. This process of rearranging, of seeking a lower energy state, is the key to everything that follows. It is the secret that, when placed under pressure, will unlock an entirely new reality for water. We have seen what happens with small changes in contact and temperature. But that is only the first step. What happens when we look at the process of freezing itself? The unseen dance of freezing. We say water freezes at 0 degrees Celsius or 32 Fahrenheit. But that is one of the most common simplifications in science. The truth is, pure water does not want to freeze. It can remain liquid well below its freezing point, in a fragile state known as being supercooled. It can reach temperatures as low as -40 Celsius and still be a liquid. To freeze, water needs a reason. It needs a trigger. This is called a nucleation site. It can be a microscopic impurity, a speck of dust, or even just a small imperfection on the surface of its container. Without a nucleation site, the water molecules exist in a state of chaotic, random motion. They are constantly moving, bumping into one another. Every so often, by pure chance, a few molecules will happen to collide in just the right orientation to form a tiny, fleeting seed of a crystal. But these small clusters are fragile. The random thermal energy of other molecules usually breaks them apart before they can grow. Think of frost forming on a window pane. It does not appear everywhere at once. It begins from a single point, a tiny imperfection in the glass, and from there, it spreads outward in delicate, branching patterns. That single starting point is all that is needed. This is what happens in supercooled water. Once a random collision creates a seed crystal that is large enough, a critical nucleus, it triggers a quiet chain reaction. The surrounding liquid water molecules, which were waiting for an ordered pattern to follow, rapidly arrange themselves around the seed. A wave of crystallization spreads through the water, turning liquid into a solid. And the solid it forms is, for the most part, the ice we know. Scientists call it ice. The H stands for hexagonal. This is the most common form of ice on Earth. The reason it's hexagonal comes down to the V shape of the water molecule itself. Through a force called hydrogen bonding, each of these molecules connects to 4 of its neighbors in a specific tetrahedral arrangement. When you stack these arrangements together, the lowest energy, most stable structure they naturally form is a hexagonal lattice. This is the fundamental reason why no 2 snowflakes are alike, but almost all of them have 6 sides. Their intricate patterns are a macroscopic expression of this invisible, hexagonal dance of molecules. But this is not the only way. Even under conditions we might consider normal, nature has another form. In the cold of the upper atmosphere, water vapor can sometimes form a different structure known as ice. The C stands for cubic. It's a slightly different arrangement of the same water molecules, stacking into a diamond-like cubic pattern. Ice is what's known as metastable. It can exist, but it is not the most stable form. Given the slightest opportunity, it will spontaneously flip its structure back to the more comfortable hexagonal arrangement. So even here, in our own atmosphere, we have proof that ice is not just one thing. We have ice in our freezers and glaciers, and we have fleeting ice in the clouds high above. The idea that a single substance can have multiple solid forms is called polymorphism. And for water, this is just the beginning. We have seen how ice forms and how it sticks together. We have learned that its structure is the result of a delicate dance. But so far, we have only been observing at the comfortable atmospheric pressure we experience every day. Temperature is only one dial we can turn. The other is pressure. And when we start to turn that dial, the familiar world of ice dissolves, and we enter a realm that is truly, quietly strange. A world under pressure. To understand what comes next, we need to look at a special kind of map. It is called a phase diagram. For any substance, a phase diagram shows you what state it will be in, solid, liquid, or gas, at any given combination of temperature and pressure. For most materials, the map is simple, with 3 clear territories. But for water, the phase diagram is an intricate landscape of possibilities. It is one of the most complex and studied maps in all of materials science. The reason for this goes back to one of water's most famous properties. Most substances become denser when they freeze. But water does the opposite. It expands. The hexagonal lattice of the ice in your freezer is a very open structure, with a great deal of empty space built into it. This is why ice floats. It is less dense than the liquid water it displaces. This property is essential for life on Earth, allowing lakes and rivers to freeze from the top down, insulating the life below. But from a physics perspective, it is a profound anomaly. And this anomaly is the key to everything that follows. What happens when you take this open, spacious crystal and begin to squeeze it? Imagine applying immense pressure. Physics does not favor wasted space. Under this force, the open, hexagonal structure of ice becomes unstable. It cannot withstand the compression. The hydrogen bonds that hold it together buckle. But the water does not simply melt. Instead, the molecules do something extraordinary. They rearrange themselves. They find a new, more compact way to stack together, forming an entirely new crystal structure. They become a new phase of ice. A denser phase of ice. If we take normal ice and increase the pressure to about 2,000 times the atmosphere around us, ice collapses and transforms into ice 3. This ice is about 10% denser than liquid water, so it would sink. This has fascinating implications. Because it is a compressed form, it doesn't expand upon freezing. Scientists have studied this kind of pressure-induced freezing for cryopreservation, as it would not damage living cells with expanding ice crystals the way normal freezing does. If we turn the pressure dial higher, at around 3,000 atmospheres, we meet ice V. At 6,000 atmospheres, we find ice V. Each of these is a distinct solid phase of water, with a unique crystal structure, more complex and more densely packed than the last. These are not just laboratory curiosities. Scientists believe these forms of ice may make up a significant portion of the interiors of the large, icy moons of our solar system, like Jupiter's Europa or Saturn's Titan. Deep beneath their shells of normal ice, the immense pressures could be squeezing the water into these exotic, sinking ice phases. All of these phases are made of the same water molecules, but the final structure is completely different. Scientists have been discovering these new forms for more than a century, each one a new landmark on the strange map of water. For a long time, we knew of about 17 or 18 distinct phases. But the exploration is far from over. In recent years, new phases have been found, sometimes existing for only fleeting moments in experiments, revealing that even the map we have is incomplete. So far, we have met only a few of ice's other forms, born from pressures found deep within planets and moons. And it already changes what we thought we knew. The idea that such a simple substance can have so many different solid forms is quietly mind-boggling. If this kind of exploration into the nature of things helps you see the world differently, consider subscribing to the channel. We often peel back the layers of simple questions, following them to unexpected and beautiful answers. Now, let us turn the pressure much higher. Let us go from the pressures at the bottom of an ocean to those near the center of a planet. This is where ice stops being just a rearranged crystal and becomes something else entirely. The diamond anvil and the alien ices. To explore these extreme realms, scientists use a special tool. It is called a diamond anvil cell. It is a quiet marvel of engineering. The concept is surprisingly direct. Two flawless, brilliant cut diamonds are mounted tip to tip. A microscopic sample of water is placed in a tiny chamber between them. Then, a screw is turned. Because the tips of the diamonds are so small, even a modest force is concentrated into an immense pressure, greater than that found at the center of the Earth. Diamonds are used for a simple reason. They are the hardest known natural substance, and they are transparent, allowing scientists to see what is happening to the sample trapped inside. With this device, we can watch what happens to water on a journey to the deep Earth. As we increase the pressure past 24,000 atmospheres, we enter the domain of another phase, Ice 7. Ice 7 is special. It has a simple cubic crystal structure and it is remarkably stable over an enormous range of pressures and temperatures. And we know for a fact that it exists deep within our own planet. In 2018, scientists studying diamonds that had erupted from the Earth's mantle, from depths of over 600 kilometers, made a remarkable discovery. Trapped inside these diamonds were microscopic pockets of Ice 7. Consider what this means. A diamond, a crystal of carbon, formed deep in the Earth. As it grew, it trapped a tiny droplet of water. The diamond was then carried to the surface. It is so strong that it acted as a tiny, natural pressure vessel, maintaining the immense pressure on the water inside it, even as the whole system cooled. What was liquid water deep in the mantle became a crystal of Ice 7, perfectly preserved. It was the first direct evidence for the presence of water in the deep mantle, a profound discovery for understanding the geology of our planet. But we can go further. We can keep squeezing. As we push past 1 million atmospheres of pressure, water undergoes a transformation that is less about geometry and more about fundamental physics. We arrive at a phase called Ice X. To understand Ice X, you must remember the bonds that hold water together. In a normal crystal, a hydrogen atom is shared between 2 oxygen atoms, but it stays much closer to its home, oxygen. In Ice X, the pressure is so great that it forces the oxygen atoms so close together that the hydrogen atom has no choice. It positions itself exactly halfway between them. The distinction between the bond holding the molecule together and the bond linking it to its neighbor vanishes. They become one and the same, a perfectly symmetric bond. The water molecule as we know it essentially ceases to exist, replaced by a symmetric crystal of atoms. It is a truly exotic state of matter. Even beyond this, at pressures of millions of atmospheres, research suggests that even this structure breaks down, with the atoms organizing into bizarre, kinked chains. The very rules of how water organizes itself are still being discovered in laboratories around the world. We have journeyed from our freezer to the core of our own planet. We have seen ice become denser than rock, and transform its very chemical bonds into something new. But the most shocking transformation, the one that seems to defy all logic, happens when we combine these immense pressures with unimaginable heat. The climax, ice hotter than the sun. How can ice be hot? The word itself is synonymous with cold. This is where we must adjust our definitions. In physics, ice does not strictly mean cold. It means that the atoms of a substance are arranged in a fixed, ordered, crystalline lattice. It is about structure, not temperature. And that brings us to a state of matter predicted in the 1980s, but only confirmed in a laboratory in 2018. Superionic ice, also known as Ice 18. It forms under conditions that are difficult to imagine. Pressures of millions of atmospheres and temperatures of thousands of degrees Celsius. These are the conditions believed to exist deep inside the ice giant planets, Uranus and Neptune. So what is it? Under this combination of extreme pressure and heat, water does something unprecedented. The immense pressure forces the heavy oxygen atoms to lock into place. They form a rigid, solid, crystalline lattice, just as in any other form of ice. That is the ice part. But the temperature is so incredibly high that the lightweight hydrogen atoms have too much energy to stay put. They break free from their oxygen partners. They detach and begin to flow like a liquid through the solid, unmoving cage of oxygen atoms. Superionic ice is a state of matter where a solid and a liquid exist in the same space at the same time. A solid lattice of oxygen, through which flows a liquid sea of hydrogen protons. And because those flowing protons are charged particles, this flowing sea creates an electric current. Superionic ice is an electrical conductor. For this reason, it is sometimes described as a strange, hot, black ice. But what of the claim that it can be hotter than the sun? In experiments at facilities like the Lawrence Livermore National Laboratory, scientists fire some of the world's most powerful lasers at a tiny droplet of water. This creates a shock wave that simultaneously compresses and heats it for a few billionths of a second. In those fleeting moments, they have successfully created superionic ice at temperatures approaching 5,000 degrees Kelvin. The surface of the Sun is approximately 5,778 Kelvin. So, yes, for a brief instant, a form of ice has been created in a laboratory at a temperature that rivals the surface of our star. This is not just an intellectual curiosity. The existence of superionic ice may solve a long-standing mystery. The planets Uranus and Neptune have bizarre magnetic fields. They are lumpy, uneven, and tilted away from the planet's rotation. Scientists now believe that these strange magnetic fields are generated by a vast layer of superionic ice deep within these planets. The constant, flowing sea of charged hydrogen inside that ice acts as a massive dynamo, generating the weird, chaotic magnetic fields we observe from so far away. This bizarre form of ice, born of impossible heat and pressure, is shaping entire worlds. Let us return to where we started. Your freezer. That simple, mundane act of two ice cubes sticking together. It seemed like a small thing. But it was not. It was a clue. It was a quiet signal that the molecules that make up the ice in your glass are restless, always moving, rearranging, and seeking a more stable state. We followed that single clue on a journey from the kitchen counter, down through the clouds, and deep into the crushing pressure of the Earth's mantle, where we found ancient ice trapped in diamonds. From there, we pushed further, into the realm of diamond anvils and symmetric bonds, and finally out across the solar system to the cores of giant, distant planets. Along the way, we discovered that water does not have just one solid form, but a family of at least 20 of them. We found ice that sinks, ice that forms in a cubic pattern, ice that has no memory of ever being a water molecule, and finally, a strange, hot, black ice that conducts electricity and generates the magnetic fields of planets. The ice cube slowly melting in your drink is just the beginning. It is phase 1, Ice IH. It is the humble ambassador for one of the most versatile, strange, and cosmically important substances in the universe. It shows how many incredible secrets are hiding all around us, in the most ordinary things, waiting for a question to be asked. What seems simple on the surface is almost always a doorway to a universe of complexity and wonder. What part of this journey resonated with you the most? The fact that ice can exist deep inside a diamond? The idea of a symmetric ice that forgets what a water molecule is? Or the hot, black, superionic ice that may be shaping distant worlds? Feel free to share your thoughts in the comments below. And if you want to continue exploring the hidden science of the everyday, make sure you subscribe so you don't miss the next journey. Ice's fatal flaw is hiding in plain sight. For a long time, the explanation has seemed simple. It is just thermal shock, the outside of the ice changing temperature far faster than the inside. And that explanation is not wrong, but it is not the whole story, either. The simple story of temperature difference is just the opening act. The real reason ice shatters so unpredictably is a flaw written into its very structure from the moment it froze. The breaking point is not created by your drink. It has been there all along, hiding in plain sight. And understanding it reveals a hidden, chaotic world inside one of the most common substances on Earth. Welcome to the Sleepy Scientist. If this kind of calm exploration into the world around us helps you unwind, consider liking the video and subscribing to the channel. The obvious answer, and why it's incomplete. Let's begin with the explanation we all reach for: thermal shock. It is intuitive, it makes sense, and it is, without a doubt, a huge part of the story. When you take an ice cube from a freezer, it might be as cold as -18 degrees Celsius. Your drink, even chilled, is dramatically warmer. When that liquid cascades over the ice, the very outer surface experiences a rapid change in temperature. At a molecular level, temperature is motion. The water molecules in the cold ice are locked into a rigid structure, vibrating in place. As the warmer liquid transfers its heat, the outer molecules of the ice absorb this energy and begin to vibrate more aggressively. This causes the surface to try and change its size. The problem is, heat takes time to travel. While the surface is experiencing this sudden jolt, the core of the ice cube is still deep frozen, unaware of the chaos on the outside. So you have a conflict within the ice itself. The outer layer is trying to rapidly change its shape and size, while the cold, dense interior refuses to budge. This creates an immense amount of internal stress. Ice, for all its apparent strength, is a brittle material. It cannot bend or stretch to accommodate this stress. It can only do one thing: break. The cracking sound you hear is the sound of the ice violently relieving that internal pressure. This is a perfect, logical explanation. It explains why colder ice and warmer liquids create more dramatic cracks. The temperature difference is steeper, leading to more stress. But, if that were the whole story, the world would be a much more predictable place. If thermal shock were the only factor, then two identical ice cubes, from the same tray, should behave in roughly the same way. But they do not. One might split cleanly in two. Another might splinter into a dozen tiny shards. A third might just sit there, stubbornly refusing to crack at all. Why the inconsistency? Thermal stress provides the asterisk force, the why, of the crack. But it does not explain the asterisk path, the where. The stress does not just create a crack out of thin air. It exploits a weakness that is already there. To find that weakness, we have to look deeper. We have to stop thinking of ice as just a uniform, solid block and start thinking of it as what it truly is: a crystal. And like many crystals, its perfection is often an illusion. Peeling back the layers, ice as a crystal. When we say something is a crystal, we mean it has a highly ordered internal structure. Its molecules are not a jumbled mess. They are arranged in a precise, repeating pattern, like bricks in a perfectly constructed wall. This underlying pattern is called a crystal lattice, and it is what gives crystals their characteristic flat faces and sharp angles. The shape you see on the outside is a reflection of the order on the inside. The building block of an ice crystal is the water molecule, H2O. Its shape is the key. The two hydrogen atoms are attached to the oxygen atom in a V shape, which makes the molecule polar. The oxygen side has a slight negative charge, while the hydrogen side has a slight positive charge. Just like tiny magnets, these positive and negative ends are attracted to each other. This attraction is called a hydrogen bond. And when trillions of them work together, they are more than strong enough to lock the molecules into a solid structure. And this structure is breathtakingly elegant. In the ice you find in your freezer, the water molecules arrange themselves into a hexagonal lattice. This is the most stable form of ice on Earth, known as asterisk ice IH. The H stands for hexagonal. Imagine looking down on a single layer of these molecules. You would see them forming interconnected, six-sided rings. Now, imagine stacking these layers. They follow a specific rhythm. A layer we can call A, followed by a slightly offset layer, B, then another A layer, then another B, and so on. This above stacking pattern gives rise to the six-fold symmetry so famously visible in snowflakes. This hexagonal structure has a fascinating and crucial consequence: it is surprisingly full of empty space. This is why ice is less dense than liquid water, an incredibly rare property. When ice melts, the rigid structure collapses, and the molecules can pack closer together. It is why ice cubes float. So, in a perfect world, every ice cube would be a flawless crystal of ice IH, a single structure with every molecule in its designated place. If you applied thermal stress to this perfect crystal, it would be incredibly strong. But the ice in your glass is not from a perfect world. It was born in haste, and its creation was a messy, chaotic affair. And in that chaos lies its flaw. The rival, a different way to build with water. Nature, it turns out, has more than one way to build a crystal of ice. While the hexagonal above pattern is the most stable, it's not the only option. There is a rival structure, a different way of stacking those same layers. Instead of the two-step above rhythm, this form follows a three-step pattern. ABC. This creates a crystal with a cubic symmetry, and so it is known as *ice. So where do you find this cubic ice? Generally, not in your freezer. Ice is what scientists call metastable. It is like a ball resting in a small dip on the side of a hill, rather than at the bottom. It can exist, but with a little nudge, a bit of heat or time, it will settle into the more stable hexagonal form. Cubic ice tends to form under specific conditions, like when water vapor freezes at extremely low temperatures, high in Earth's atmosphere. The very existence of pure cubic ice is a subject of scientific debate. Some research suggests that what we call cubic ice might be something even more complex. But for our purposes, the crucial takeaway is this: there are at least two competing ways for water molecules to organize themselves. There is the stable, hexagonal way, and the less stable, cubic way. This rivalry is the key. Because when water freezes in the real world, not in a pristine laboratory, but in an ice cube tray, the process is a frantic race against time. Molecules are being locked into place with incredible speed. And in this rush, no single, perfect structure wins. Instead, what you get is a compromise. A series of mistakes. A flaw built into the crystal from the very beginning. The reveal, the flaw of imperfection. We now have all the pieces. We have the force, thermal shock. We have the building blocks, water molecules. And we have the competing blueprints, the hexagonal form and the cubic form. Now, we bring them all together. Imagine a builder tasked with constructing a wall, and they have to do it as quickly as possible. They have two sets of instructions, one for an above pattern and one for an ABC pattern. In their haste, they do not stick to one. They lay a few rows in the above pattern, then accidentally switch to the ABC pattern, then switch back. The wall gets built, and from a distance, it looks solid. But the builder knows that at every point where the instructions changed, a seam of imperfection was created. This is what happens when an ice cube freezes. When water freezes quickly, the molecules do not have the time or energy to find their perfect, most stable hexagonal positions. They lock into place through the easiest and fastest option available. The result is what scientists call * stacking disordered ice. It's not pure hexagonal or pure cubic. It's a chaotic jumble of both. You have a few layers in the hexagonal sequence, and then, a mistake happens, and a layer initiates a brief sequence of cubic stacking. The boundary where one stacking sequence switches to another is a crystal defect known as a * stacking fault. It is a literal one-molecule thick plane of error. But this is just one example. The rapid, uneven cooling in a freezer means the water does not form one beautiful crystal. It forms a multitude of small crystals that crash into each other, creating even more boundaries and defects. The final ice cube is a composite material, held together by these seams of weakness. So, the ice cubes you drop into your glass are not perfect, crystalline gems. At a molecular level, they are a chaotic landscape of imperfections. They are born broken, preloaded with microscopic fault lines that are just waiting for the right kind of stress. The crack that you see is not being created in that moment, it is being revealed. The proof: connecting the flaw to the crack. Now, let's return to our ice cube. It looks solid, but we know its secret. It is riddled with these invisible, molecular-scale planes of weakness. And now, we pour in the drink. The warm liquid initiates the thermal shock. The outer surface wants to change size, while the inner core remains rigid. This creates a powerful wave of stress that propagates through the crystal. In a perfect, flawless crystal, that stress would be distributed evenly. But our ice cube is far from perfect. As the stress wave travels, it is moving through a landscape filled with pre-existing weaknesses. The energy of the stress wave naturally seeks the path of least resistance. The distorted, strained bonds along these defects are that path. The force becomes intensely concentrated along these microscopic fault lines. And then, crack. The sound you hear is the sound of the crystal failing along that pre-existing flaw. The crack does not appear in a random location. It follows the precise geometry of the defects created when the ice first froze. This single concept explains the unpredictability. Why does one ice cube split cleanly in half? It likely had one large, well-defined defect running through it. Why does another shatter into a mess of tiny pieces? It was likely riddled with countless small defects pointing in all directions. The stress branched out, following every available path. And why does a third ice cube refuse to crack? It might have frozen more slowly, allowing it to form with far fewer defects, its internal structure strong enough to withstand the shock. The mystery is solved. The crackling of ice is not just a story of temperature. It is a story of history. It is the sound of an imperfection, locked into the crystal's structure from its birth, finally giving way. The sound is an echo of the moment the ice was made. Wider implications and the ice menagerie. This hidden flaw in everyday ice is fascinating, but the same principles of crystal defects have consequences for our entire planet. Let's move from an ice cube to the massive ice sheets of Antarctica and Greenland. These glaciers are, in essence, unimaginably huge ice crystals. And just like our ice cubes, they are not perfect. As snow compacts into ice, stresses create and align these same kinds of defects on a massive scale. These become vast zones of internal weakness that can precondition the ice for failure. When the Larsen B ice shelf underwent its dramatic collapse in 2002, it was a catastrophic failure that likely involved the exploitation of such pre-existing weaknesses. This is central to a concept that climate scientists are studying today: marine ice cliff instability or MICI. The idea is that as warming oceans expose massive, vertical cliffs of ice, the cliff's own weight can create so much stress that it overwhelms the inherent strength of the ice, causing it to collapse. The ultimate strength of that ice is dictated not just by its size, but by the network of hidden flaws within its crystalline structure. Understanding the flaw in a tiny ice cube helps us model the potential collapse of a continent-sized ice sheet. But the story gets even weirder. Ice IH and Ice IC are just the beginning. Water is a molecular shapeshifter. By subjecting it to immense pressures, scientists have confirmed at least 19 other crystalline phases of ice. These likely exist in the universe. Increase the pressure, and you get phases like Ice 3 or Ice V, which may make up the thick ice mantles of moons like Ganymede. Crank the pressure to hundreds of thousands of atmospheres, and you can form Ice 7 or even Ice X, where the very concept of a water molecule begins to break down. Under even more extreme conditions, you might get superionic ice, where oxygen atoms form a lattice, but hydrogen ions flow through it like a liquid. This bizarre substance may well exist in the cores of Uranus and Neptune. The entire field of metallurgy, the science of making metals strong, is fundamentally the study of controlling crystal defects. The strength of a steel beam is determined by fine-tuning its crystalline grain boundaries, which are analogous to the flaws in our ice cube. By understanding why your ice cracks, you're touching upon a universal principle that governs the strength and failure of materials all around us. So, let's return to our simple glass. The next time you drop ice into a drink and hear that satisfying, sharp crackle, you will know the full story. You will know it is not just the cold. That sound is the final, audible gasp of a hidden, fatal flaw. It is the sound of an imperfection at a molecular level, a mistake made in the chaotic rush of freezing, finally giving way. The sound you hear is a story that began the moment that ice was born, a story of order, chaos, and the quiet, unpredictable weakness hiding in plain sight. If you have enjoyed this exploration, please consider subscribing to the channel for more content like this. And if you have a topic you would like to hear about, please feel free to leave a comment below. Until next time, stay sleepy and stay curious. The bizarre reason ice floats and saves the world. It is one of the most familiar sights in our world. An ice cube in a glass of water. It seems simple, even unremarkable. And yet, what we are observing is something quietly strange. An exception to a rule that governs almost everything else we know. Almost every other substance, when it cools from a liquid to a solid, becomes more compact, more orderly. The molecules settle into a dense arrangement, and the solid sinks in its own liquid. Molten iron, once cooled, sinks. Paraffin wax, solidified, will drop to the bottom of the melted wax. This feels intuitive. The chaotic energy of a liquid gives way to the dense, packed order of a solid. So why does water not follow this rule? Why does it do the opposite? The answer is not simply a curious fact. It is a story of invisible forces, geometric precision, and a molecular property with consequences the size of a planet. It is perhaps the single most important physical anomaly for life as we know it. The reason ice floats is the same reason our world is a living one, and not a frozen, sterile sphere. By the end of this exploration, you may never look at a simple glass of water the same way again. To understand this mystery, we first have to appreciate how unusual it is. In the universe of substances, the shift from liquid to solid is a story of order taking hold. In a liquid, molecules are like a crowd, close together but moving past one another without a fixed structure. There is energy and disorder. Cooling the liquid is like asking that crowd to settle down. The molecules lose energy, their movement slows, and they pack themselves together as efficiently as possible. This is almost always a denser, crystalline solid. More material in less space. This rule is followed with remarkable consistency. A block of solid steel is denser than molten steel. The same is true for lead, for alcohol, for nearly any substance we can name. The solid form is the dense form. The solid form sinks. And then there is water. The one substance that, upon feeling the pull of this universal tendency, seems to go the other way. When liquid water freezes, it does not become more dense. It becomes less dense, by about 9%. It expands. It takes up more space. And because it is less dense than the water around it, it floats. This is not a small statistical variation. It is a fundamental reversal of a physical law. To understand why, we have to look for clues not on a scale we can see, but a billion times smaller, in the world of the molecule itself. Every great mystery has a central character, whose hidden nature is the key to the puzzle. In this story, it is the water molecule, hydrogen oxide. On the surface, it seems simple. One oxygen atom and two hydrogen atoms. But its nature is revealed not in its parts, but in its shape. The first thing to understand is that the hydrogen oxide molecule is not a straight line. It is bent. The two hydrogen atoms attach to the oxygen atom at an angle of about 104.5 degrees, giving the molecule a distinct V-shape. This shape is a direct result of the oxygen atom's nature. Oxygen is a highly electronegative atom, meaning it pulls shared electrons more strongly toward itself. In the bonds within a water molecule, the powerful oxygen atom draws the electrons from the two hydrogen atoms closer. The electrons spend more of their time around the oxygen nucleus than they do around the hydrogen nuclei. This unequal sharing creates something important, polarity. Because the negative electrons gather around the oxygen atom, that end of the molecule holds a slight, persistent negative charge. The hydrogen atoms, in turn, are left with a slight, persistent positive charge. So, the water molecule is not a neutral ball. It is a tiny, V-shaped object with two distinct poles. A negative pole at the oxygen corner, and positive poles at the hydrogen corners. This polarity is the hidden trait that drives all of water's unusual behavior. Most other common liquids are made of nonpolar molecules, which are more symmetrical, with charge distributed evenly. But water has this built-in electrical character. It is the source of its strangeness, and it is what allows one water molecule to interact with another. Those interactions are the basis for our next clue, a hidden force that orchestrates everything that follows. If the molecule's polarity is its character, then hydrogen bonds are the connections it forms. This is our second major clue, an invisible architecture that dictates how water molecules arrange themselves. It is a force born entirely from the polarity we just discussed. Imagine a space filled with these tiny, polar molecules. The slightly negative oxygen end of one is gently attracted to the slightly positive hydrogen end of a neighbor. This attraction is called a hydrogen bond. It is not as strong as the bonds holding the molecule itself together. Those are intramolecular, happening within the molecule. Hydrogen bonds are intermolecular, happening between molecules. They are weaker, more fleeting, but they are the reason liquid water holds together. In liquid water, this network of hydrogen bonds is a quiet, constant dance. Molecules are always moving, energized by heat. Hydrogen bonds form, break, and reform in trillionths of a second. A molecule connects with a neighbor for a moment, only to be nudged away and form a new bond with another. The molecules can still slide past one another, which is what makes water a liquid, but they are always tugging on each other in a dynamic, ever-changing web. This constant connection is what gives water its cohesiveness, why it forms droplets and has surface tension. Now, let's lower the temperature. As heat is removed, the molecules lose kinetic energy. The dance slows. And as the molecules move less, the hydrogen bonds begin to exert more influence. The fleeting connections start to hold for longer. This brings us to a crucial point in our story: water's behavior at 4 degrees Celsius. As water cools, it behaves normally at first. It contracts and becomes denser. But this trend stops and reverses at 4 degrees Celsius. At this temperature, water reaches its maximum density. Below this point, as it gets colder, it starts to expand and become less dense. This is completely backward. What is happening is that at 4 degrees Celsius, the molecules have slowed enough for the hydrogen bonds to start winning the battle against random motion. The molecules begin to form more structured, open arrangements that are a preview of the structure of ice. As the temperature drops further towards 0 degrees Celsius, thermal motion becomes so weak that the hydrogen bonds can dictate a much more rigid and orderly structure. The connections are about to lock into place. This is where we find the final piece of our puzzle, the solution to the entire mystery. We have gathered the clues. We have our central character, the polar, V-shaped water molecule. We have the hidden force, the organizing power of the hydrogen bond. Now, we witness the event itself, the freezing of water. This is the moment a new kind of order emerges, one that overturns the usual rules of physics through an act of pure geometry. As the temperature hits 0 degrees Celsius, the molecular dance almost halts. The hydrogen bonds are no longer fleeting, they become the dominant force, locking each molecule into a fixed position. And they do so in a very specific way. They orchestrate the formation of a highly ordered, three-dimensional crystal lattice. Here is the quiet, bizarre reason ice floats. Because of the water molecule's bent shape and the specific angles of its bonds, the most stable structure they can form is an open hexagonal lattice. In this rigid crystal, every water molecule is hydrogen bonded to 4 others in a precise arrangement. This structure is beautiful. It is orderly. But it is not compact. The geometry of the hydrogen bonds forces the molecules to hold each other at a distance. They cannot pack together closely as they could in the disordered liquid state. Instead, they are locked into a formation that creates a significant amount of empty space within the crystal. The structure is full of hexagonal channels and open pockets. This is the climax of the story. This is why ice is less dense than water. The molecules in solid ice are, on average, farther apart than the molecules in liquid water. When water freezes, its volume expands by about 9%. More volume for the same mass means lower density. And lower density means it floats. It is a quiet paradox. The transition from the chaos of a liquid to the order of a solid, which for nearly every other substance means packing more tightly, for water means spreading out. The very act of becoming an ordered crystal forces it to become spacious. This hexagonal lattice is the molecular architecture of this strange behavior. It explains why a can of soda left in the freezer expands and bursts. It explains the six-sided symmetry of a snowflake, a macroscopic echo of the invisible crystal structure. The mystery is solved. Ice floats not in spite of becoming an ordered solid, but because of it. The polarity of the water molecule gives rise to hydrogen bonds, and these bonds, when they freeze, achieve stability only by building a spacious, open lattice that is less dense than the jumbled liquid it came from. Now we can zoom out. We have solved the molecular puzzle, but what are the consequences of this unusual property? They are not just interesting, they are profound. The fact that ice floats is one of the most critical factors that allows life to exist on Earth. Let us begin with a thought experiment. What if water behaved like a normal substance? What if ice were denser than liquid water and sank? Imagine a lake in winter. As the cold air chilled the surface, it would freeze. That new ice, being dense, would sink to the bottom. Then, the next layer of water would be exposed to the cold, and it too would freeze and sink. This process would repeat. Over time, the entire lake would become a solid block of ice from the bottom up. Any life within it would be trapped and frozen. In any climate with a winter, life in freshwater would be impossible. But that is not what happens. Because ice is less dense, it forms a layer on the surface. This layer then acts as an insulating blanket, protecting the liquid water below from the much colder air above. Ice is a poor conductor of heat. So even if the air temperature drops far below freezing, the great volume of the lake remains liquid and protected. The process is even more elegant. Remember that water is densest at 4 degrees Celsius. This means that in a winter lake, the coldest water, at 0 degrees Celsius, near the ice, is at the top, while the heaviest water, at 4 degrees Celsius, sinks to the bottom. This creates a stable environment where aquatic life can survive the winter, waiting in the relatively mild 4-degree water at the lakebed. This simple act of floating ice turns our planet's lakes and ponds into winter refuges instead of tombs. Now, let us scale this up to the entire planet. The same principle applies to our oceans and polar ice caps. The vast sheets of sea ice in the Arctic and Antarctic float on top of the ocean. This has world-altering consequences. First is the albedo effect. Albedo is a measure of how much sunlight a surface reflects. Bright, white surfaces like ice have a high albedo. They reflect a large amount of solar energy back into space. Dark surfaces like the open ocean have a low albedo. They absorb most of the sun's energy as heat. The massive, floating ice sheets at our poles act as the planet's reflective shields. They play a crucial role in regulating Earth's temperature by bouncing solar radiation away, helping to keep the planet cool. If ice sank, this effect would be lost. The darker ocean would absorb far more heat. Furthermore, a world with sinking ice would eventually become a very different kind of planet. As ice sank to the bottom of the oceans, it would accumulate in the cold, dark depths. Away from the sun's warmth, this deep ocean ice would be incredibly slow to melt. Over long stretches of time, the oceans could fill with ice from the bottom, potentially turning Earth into a frozen world and extinguishing most marine life. The existence of a stable, liquid water planet hinges on this single, strange property. From the smallest pond to the largest ocean, from the survival of a single fish to the regulation of the entire global climate, the fact that ice floats is a cornerstone of our living world. All of this traces back to a single detail: a bent molecule with an uneven charge, forcing itself into a spacious, elegant crystal. The world around us is filled with these hidden stories, quiet scientific truths hiding in plain sight. What seems mundane is often a window into the extraordinary rules that govern our universe. If this kind of calm exploration helps you unwind, consider liking the video and subscribing to the channel. So, the next time you drop an ice cube into a drink and watch it bob to the surface, take a moment to appreciate what you are witnessing. You are not just looking at frozen water. You are watching the result of a molecular structure so particular, so perfectly arranged in its hexagonal form, that it becomes less dense as a solid than as a liquid. It is no small quirk. It is the molecular property that allows life to survive the cold, that insulates our lakes, and that helps regulate our planet's temperature. It is a story of polarity, of hidden forces, and of a geometric masterpiece built by hydrogen bonds. It is the quiet, beautiful, and world-saving reason that ice floats. Antarctica's Doomsday Glacier is a ticking time bomb. Deep in the most remote part of our planet, in a landscape of immense silence and hostility, a single body of ice is beginning to stir. It rests in West Antarctica, a frozen giant that, for millennia, has moved in geological time. But that quiet movement is quickening. Its vast structure is showing signs of failure. And within its frozen heart, it holds enough power to redraw the coastlines of the world as we know it. Scientists have given it a name that reflects this power: the Doomsday Glacier. This is not a work of fiction. The Thwaites Glacier is a present-day reality, and the forces driving its decay are unfolding now, with consequences that will be felt on every continent. This single glacier has become a focal point for our planet's future, a kind of ticking clock. In this video, we're going to explore the fragile physics of why it's so unstable, what makes it so profoundly dangerous, and why that ticking seems to be getting louder. The Thwaites Glacier's scale is difficult to hold in the mind. It covers an area roughly the size of Great Britain or Florida. It is one of the widest glaciers on Earth, a river of ice over 100 kilometers across that pours into the Amundsen Sea. But its surface area alone does not capture the true nature of its importance. The greater danger lies in what it holds back. Imagine a bottle of champagne. Thwaites is the cork. Behind it, the rest of the West Antarctic ice sheet sits waiting, a colossal volume of ice that, if released, contains enough water to raise global sea levels by a catastrophic 10 feet, or 3 meters. Thwaites Glacier is the gatekeeper, the plug holding back a global flood. And for a long time, scientists have watched as that plug begins to crumble. Recent discoveries have turned that quiet concern into genuine alarm. The glacier is losing ice at an accelerating rate, currently shedding about 50 billion tons of ice into the ocean every single year. That loss alone now accounts for a staggering 4% of all annual global sea level rise. The Doomsday moniker isn't for sensationalism. It's rooted in scientific concern about the glacier's foundational role in the stability of our planet. The clock is real, and to understand just how it works, we have to journey to the front lines of climate science, to the very edge of the world. The problem: a giant in retreat. So what, exactly, is happening to this frozen behemoth? The story of Thwaites is a story of accelerating retreat. For thousands of years, the glacier existed in a state of relative equilibrium, its immense weight balanced by climate and geography. But in an age of warming, that balance has been disturbed. Satellite observations over the past few decades paint an unambiguous picture. The glacier is thinning, flowing faster, and its edge is pulling back from the sea. Its grounding line, the critical point where the glacier lifts off the bedrock and begins to float, has retreated significantly since the late 1990s. This may not sound like much in human terms, but in geological time, it is a full-blown sprint. Glaciers are meant to change on timescales of centuries or millennia. Thwaites is changing on the timescale of a human lifetime. The volume of ice being lost is almost impossible to comprehend. Recent studies have shown that Thwaites is now losing ice faster than at any point in the last 5,500 years. This isn't just about a single glacier melting. It's about a fundamental shift in the dynamics of an entire ice sheet. The cork in the bottle analogy is profoundly accurate. Thwaites acts as a physical barrier, a buttress that slows the flow of the vast sea of ice behind and around it. As Thwaites weakens, its ability to hold back this inland ice diminishes. Its retreat could trigger a domino effect, potentially destabilizing a vast region of West Antarctica. The problem is clear and present. A giant is not just stirring, it is actively shrinking and weakening before our eyes. Its foundations are being eaten away, and its structure is beginning to fail. But to understand the true gravity of the situation, we need to understand why. The answer isn't just on the surface. It lies in the dark, cold, and incredibly hostile waters churning beneath 2 kilometers of ice. So, what's happening at the edge of the world to make this giant so unstable? The answer has required one of the most ambitious and daring scientific expeditions ever mounted. The exploration journey to the edge of the world. Studying the Thwaites Glacier is not a simple task. It is one of the most remote and inaccessible places on Earth. Reaching it requires a multi-week voyage across the stormiest seas on the planet, followed by a perilous journey across a landscape of fractured, moving ice. The conditions are brutal. Until recently, the main trunk of Thwaites was considered largely unexplored due to its chaotic and dangerous nature. Because of the immense stakes, the global scientific community has mobilized in a way rarely seen. The International Thwaites Glacier Collaboration, or ITGC, is a joint effort between the United States and the United Kingdom, bringing together hundreds of scientists in a 5-year, $50 million partnership. It is one of the largest international field campaigns ever undertaken in Antarctica, with a single, urgent goal: to understand Thwaites before it's too late. The scientists are deploying a breathtaking array of technology to peer into the glacier's secrets. They use ice-penetrating radar to map the hidden bedrock. They deploy GPS sensors to track the ice's movement with millimeter precision. They use giant hot water drills to bore hundreds of meters through the ice sheet, creating channels just wide enough to lower their instruments into the darkness below. Perhaps the most incredible tools in their arsenal are autonomous underwater vehicles, or AUVs. These robotic submarines, like the famous Bodie McBoatface and the specialized Icefin, are our robotic explorers on this alien world. After being lowered through a narrow borehole, they navigate the unseen ocean cavity beneath the glacier, traveling right up to the grounding line, a place no human has ever seen. They map the seafloor and the ice's underbelly, and they measure the temperature, salinity, and currents of the very water that is doing the most damage. This isn't just academic research. It's a reconnaissance mission into a collapsing system. Every piece of data collected is a vital clue in a planetary detective story. The scientists on these missions endure some of the harshest conditions imaginable because they know that the fate of our coastlines may depend on what they find, waiting in the dark water beneath the world's most dangerous glacier. What they have discovered has revealed a multi-pronged assault, attacking Thwaites from below and from within. The science: why it's melting. Part 1. The underbelly. The primary culprit in the rapid decay of Thwaites is not warm air melting its surface. It's the ocean. An intrusion of relatively warm, salty ocean water is attacking the glacier at its most vulnerable point, its underbelly. To understand how this happens, we need to talk about the grounding line. This is the single most important location for any marine glacier. For a glacier to be stable, its grounding line needs to be anchored on a stable piece of bedrock. But Thwaites has a fatal flaw in its geography. The bedrock beneath much of the West Antarctic ice sheet has what is called a retrograde slope. This means that as you move inland from the coast, the bedrock actually gets deeper. This is an incredibly unstable configuration. Imagine a ball perched at the top of a gentle ramp. As long as it stays put, it is stable. But give it the slightest nudge, and it will begin to roll faster and faster. Thwaites has been given that nudge. The agent of change is a mass of ocean water known as circumpolar deep water. It is only a few degrees above freezing, but in the hyper-cold environment of Antarctica, that represents a massive amount of thermal energy. Changes in wind and ocean currents are now pushing this water up from the deep ocean and funneling it directly towards the base of the glacier. Recent research has revealed this process in shocking detail. With each high tide, this warm, salty seawater is forced for miles under the part of the glacier that should be resting on the seabed. It's a daily injection of warm water far beyond the grounding line, reaching areas once thought to be protected. This warm water intrusion triggers a vicious feedback loop known as marine ice sheet instability or MISI. As the warm water melts the ice at the grounding line, the glacier's anchor point is forced to retreat inland. But because of the retrograde slope, as it retreats, it exposes an even thicker face of ice to the warm water. A thicker ice face means a larger surface area for the ocean to attack, which leads to more melting and faster retreat. It is a self-sustaining cycle of collapse. Once a glacier on a retrograde slope retreats past a certain point, it is almost impossible for it to stop. But this melting from below is only half of the story. For a long time, another, even more dramatic process of physical collapse was thought to be the greatest danger. And how our understanding of it has changed tells an important story about how science works. The science, why it's collapsing, Part 2, the cliff. Melting from below sets the stage. It weakens the glacier and forces it into an unstable retreat. But for a time, the real terror, the mechanism that could lead to truly rapid, catastrophic collapse, was thought to be what happens to the ice left towering above the water. This theory is called marine ice cliff instability or MICI. Think of ice not as a solid, but as a brittle structure. MICI is the theory that describes what happens when a glacier's front becomes a vertical ice cliff that is simply too tall to support its own weight. Scientific models suggested a critical height, beyond which the cliff face would fail, calving a massive section into the sea. This collapse would then expose a new, even taller cliff behind it, which would also be unstable. It was a potential domino effect, a feedback loop that could transition the glacier from slow melting to runaway structural failure. This was the deadly 1-2 punch that seemed to threaten Thwaites. And it was this scenario that fueled some of the most extreme projections of sea level rise. But as more data has been collected, the picture has slowly begun to change. Recent research in 2024, using new, higher-resolution computer models, has re-examined this idea. The findings suggest that this specific process, MICI, is unlikely to trigger a catastrophic collapse this century, as had been previously feared. Researchers found that as the glacier thins, it may actually reduce the height of the ice cliffs, making them more stable than older models predicted. This slow correction tells an important story, not just about Thwaites, but about how science works. Early researchers did not fail by getting it wrong. They worked with incomplete evidence and theorized the worst-case possibilities. As new data appeared, they revised their ideas and gradually converged on a more refined explanation. The glacier did not change. Our understanding of it did. The threat of MICI has not vanished, but it appears to be a less immediate danger for the 21st century. The relentless retreat from melting below, however, continues. And recent discoveries on the glacier's crucial safety brace have given scientists a new and urgent reason to worry. The ticking clock, cracks in the armor. To fully grasp the immediate danger, we need to focus on a specific part of the glacier, the Thwaites Eastern Ice Shelf, or lattice. An ice shelf is the part of a glacier that floats on the ocean. For years, the lattice has acted as a crucial buttress, a safety brace holding back the faster-flowing ice. It was held in place because it was lodged against a large, underwater mountain on the ocean floor, a pinning point that acted like an anchor. But that anchor is failing. Over the last 2 decades, scientists have watched as this critical ice shelf has begun to shatter. A network of massive cracks has been racing across its surface. These aren't small fissures. They are deep, structural rifts that slice through the shelf. Recent studies show this damage is spreading upstream into the main glacier. Sobering research has found that this destabilization is now happening largely because the ice shelf is so damaged it is beginning to tear itself apart under its own mechanical stress. It has effectively lost its grip on the pinning point that once held it fast. One lead author described it in stark terms, anticipating the ice shelf could break up within the next decade, a process that is now unfolding with alarming speed. This is the equivalent of watching the safety pins being pulled from a grenade. The collapse of this buttressing ice shelf won't by itself raise sea levels dramatically, as it's already floating. But its demise will remove the last major barrier holding back the main trunk of Thwaites. Without this resistance, the flow of the grounded ice behind it is projected to accelerate significantly, dumping even more ice into the ocean and feeding the relentless feedback loop of marine ice sheet instability. This is why scientists are watching these cracks with such intensity. They are the most visible indicator that the clock is ticking. The implication: a world redrawn. So, what happens if this process continues? What are the real-world consequences of Thwaites' retreat? The implications are global, and they would unfold over decades and centuries, irrevocably changing the world we live in. If the entire Thwaites Glacier were to disintegrate, it holds enough ice to raise global sea levels by over 2 feet, or about 65 centimeters. This alone would be a devastating blow to coastal communities. 2 feet is the difference between a manageable high tide and a destructive flood. It is enough to permanently inundate low-lying areas and contaminate freshwater supplies. But the retreat of Thwaites is only the opening act. Remember the cork in the bottle. The far greater danger is the destabilization of the entire West Antarctic ice sheet that Thwaites holds back. The complete collapse of the ice sheet contains enough ice to raise global sea levels by more than 10 feet, or over 3 meters. Let that number sink in. 10 feet. This is a world-altering transformation. A sea level rise of this magnitude would redraw the maps of our continents. Coastal cities would be lost. In the United States, Miami and New Orleans would be largely underwater. Large portions of New York City and Boston would be uninhabitable. Globally, the impact would be even more profound. Entire nations, like the Maldives and Tuvalu, would cease to exist. Huge, densely populated delta regions in countries like Bangladesh and Vietnam would be wiped out, displacing hundreds of millions of people. Historic cities like London, Amsterdam, Shanghai, and Mumbai would face an existential threat. This isn't just about flooding. It's about a cascade of secondary crises: climate refugees on a scale never before seen, immense geopolitical instability, and the destruction of coastal infrastructure triggering a global economic crisis. This is the ultimate stake. This is what the doomsday nickname truly represents. It's the potential for a global catastrophe originating from a single, failing glacier at the bottom of the world. The bigger picture: a global warning. It is tempting to view the plight of Thwaites Glacier as an isolated problem. But that would be a profound mistake. Thwaites is not an anomaly. It is a symptom. It is the clearest and most urgent signal from a planetary system under immense stress. The same forces attacking Thwaites are at play across the globe. In Greenland, glaciers are also retreating at a record pace. The same feedback loops, warming oceans attacking from below and darker, exposed surfaces absorbing more heat, are driving ice loss in the Arctic. What is happening at Thwaites is a manifestation of a global phenomenon. The world's cryosphere, its frozen regions, is in rapid retreat. Thwaites is simply showing us, in stark detail, what the endgame of ice sheet collapse looks like. Its unique and precarious geography, its immense size and its position on that unstable, retrograde slope, means that it is responding to the warming of our planet faster and more dramatically than other places. The physics are unforgiving. The feedback loops, once initiated, are incredibly difficult to stop. This brings us to the most difficult part of the story. Faced with a problem of this magnitude, it's easy to feel a sense of hopelessness. But despair is not a solution. The science of Thwaites is not meant to paralyze us with fear. It is meant to arm us with knowledge. Understanding the gravity of the situation, and understanding the mechanisms of collapse, is the absolute first step toward any meaningful response. The work of the scientists in the International Thwaites Glacier Collaboration is a profound service, providing the critical data we need to forecast our future and, hopefully, to change its course. The clock is ticking. The retreat is not a projection for the distant future, it's an observed reality. The fuse has been lit. The question that remains is whether the world will act before the warning becomes a reality felt on every coastline on Earth. The science we've explored today is the result of the tireless and often dangerous work of thousands of researchers from around the world. To see more about their incredible expeditions and to follow their latest findings, you can visit the website for the International Thwaites Glacier Collaboration. Their work is our window into this critical part of our planet. And if this kind of calm exploration into how our world is changing helps you understand it better, consider subscribing to the channel. The more we understand these issues, the better equipped we are to face them. Facing the flood. The story of the Thwaites Glacier is one of profound fragility hidden within immense scale. It is a story of how a few degrees of warmth in a distant ocean can trigger a chain reaction with the power to reshape our world. We have journeyed from the vast, frozen plains of West Antarctica to the intricate physics of ice, and the conclusion is inescapable. The Doomsday Glacier is a clear and present danger to our global society. Its fate is not a single, catastrophic event like in a disaster movie. Rather, it is a slow-motion crisis unfolding over decades, a series of tipping points that, once crossed, will lock in centuries of irreversible sea level rise. We have seen how the warm ocean is eating away at its foundations and how the last safety catches holding the glacier in check are beginning to fail. This isn't just a story about Antarctica. It's a story about Miami, about Bangladesh, about London, about every coastal community on Earth. It's a story about our global economy, our security, and the stability of our civilization in the 21st century and beyond. The future of Thwaites is not yet written in ice. The speed of its collapse is still a subject of intense scientific research. While recent findings suggest the most extreme scenarios of a sudden collapse this century are less likely, the relentless, accelerating retreat is a certainty. The choices we make today regarding global emissions will have a direct impact on how warm the oceans become, and therefore, how quickly this process unfolds. The ice is sending a message. It is communicating the profound and accelerating changes our planet is undergoing. The Thwaites Glacier is the loudest, most urgent voice in that chorus. The question is no longer if we can hear it. The question is whether we are truly listening, and how we will act, before the cliffs continue their slow, inexorable retreat into the sea.